IonQ and working as a CTO. So let's welcome our distinguished speaker today, Professor Jung-Sang Kim.
Thank you for coming. I'm going to speak in English, but we can definitely do the Q&A in Korean if you want. I prepared probably a couple hours worth of lectures, and it's a long lecture, but I want it to be more dynamic and communicative. So I'm going to pause and ask for questions. Please feel free to raise your hand. I would totally understand if after an hour you get bored and want to leave. I wouldn't be offended. All right, so let me start. Today I'm going to talk about the quantum computing with trapped ions. This is going to be more of a basic foundational lecture. Let me see if I can make this to move. I divided the 5 different topic sections. First is just a very brief introduction of quantum computers and why it's interesting. And I'm going to go through the basics of trapped ion qubits, why trapped ions are such an attractive qubit. And then the next topic would be how you would use this trapped ion technology to build a programmable quantum computer. And then I think the next are the interesting sections, which is the technology and the prospect, where we're headed. And then if we have some time, I'd really like to bring this more, in my mind, some of the most interesting progress in the last year or so is where now we can actually use this programmable quantum computer to do something very interesting and useful. Okay, so with that, let me just think about quantum computers. I'm sure all of you have heard about quantum computers. And the foundation of quantum computers are qubits. These are quantum bits instead of a binary digit, which is what a bit is. We use a quantum binary digits, which is a quantum bit. And because the power of quantum computation comes from superposition and entanglement. Now, is there anybody here who has not heard about superposition and or entanglement? Because I don't know what the audience is. Are you mostly physics majors? Everybody has taken quantum mechanics class? Anybody who has not heard about quantum mechanics? Okay, good. All right, so I'm sure you're all familiar with what a qubit is. So we need superposition, which means that you have to be able to describe a linear combination of 0 and 1. And entanglement. Entanglement means when you have more than one qubit, particularly if you have 2 qubits, there should be a entangled state where the correlation of the 2 qubits does not factor into the product of independent states. So there are many 2-level systems which can demonstrate that feature, and there's a wide range of research that's going on. But in order to then use these qubits to do computation, you have to do gate operations. Classically, we have these AND gates and NAND gates, NOR gates, very simple logic gates, where if you know what the state of the input is, then the output states are deterministically defined. Okay, and once you have a few of these logic gates, there is the universality theorem that says you should be able to build arbitrary binary operations using a very large number of these things just by concatenating them or adding them together. In a very similar way, in quantum logic gates, there are the single and multi-qubit gate operations that operate on gates. This actually has to be reversible in the sense that all quantum evolution can be time reversed. So it has to be reversible, which means that here, if you know A and B, you know the answer. But if you know only the answer, you cannot go back and deterministically identify what A and B are, meaning there's some information loss in this computation. In quantum computation, it actually has to be absolutely reversible. Okay, so there are some, and these are obviously have to be kind of time evolution of quantum physics, which is described by unitary operators and all of that. So from a physicist point of view, which I think most of us are, the most interesting things are quantum bits and logic gate operations. And if you can do single and 2 qubit gates, then you can actually do arbitrary quantum computation, which is a very, very nice result. But when you go back to this classical logic gates, that's what we know as a device physicist. But when you buy a cell phone or when you buy your laptop computer, there are computer chips in there. And the computer chip actually has to be designed to do functions. And it turns out that if you look at a real silicon chip, this is a CMOS chip, cross section, and then here they removed all of the oxides just to reveal all the wires. It turns out that the gate operations, these gates, and the transistors, they are fabricated on the surface of silicon, usually just one layer. And then you can see that there's typically like a dozen different layers of metal connecting the different transistors together. Okay, so there's just a very complex network of wires that we actually have to use to connect different transistors together. And it turns out that this laying out the wires is what circuit design is all about. So if you are a circuit designer at AMD or Intel trying to design your next computer chip, or NVIDIA, you really don't care a lot about transistors. Transistor is a black box. It's a switch that does what it does. You spend all of your time and all of your energy figuring out how to connect them, okay? Because that connectivity between transistors is actually what determines the function of your chip, okay? In classical computers, it turns out that the CMOS represents information by voltage. So if you can actually connect, the input and output with a piece of metal, then it actually transfers the information from A to B. So the wires conceptually are relatively simple, but in quantum computers, you actually have to transport this quantum information within your computer, and it actually has to support entangled states, superposition states, and all of that. So making a very large network of quantum wires that transport quantum information within your processor is not an easy task. But just like your classical processor, the way you move information around within your computer is going to be at the heart of creating functionality in your system. Okay. All right. So with that, I wanted to go back and say everybody talks about scalable quantum computers, and when you say scalable quantum computer, we usually think about lots and lots of qubits. Okay. If you think about lots and lots of qubits, I think atomic systems is the easiest because you can have lots and lots and lots of atoms. But really, when you think about scalable quantum computer, let's think about your scalable, say, your classical computer. And what does that mean? Now, of course, and how do we measure the performance of a classical computer? You can ask, of course, in one way, in Moore's law, we say the number or the density of transistors on the chip actually doubles every few years, meaning we can jam more and more transistors onto a chip. So that's a performance that's can be scalable. And then sometimes you think about things like clock speed. How quickly can you compute? How many million instructions per second of flops, floating point operations you can do. So some of these can be a measure. But really, I think what you should think about is the functional notion of scaling. Okay, functional notion of scaling means if you buy your cell phone or your smartphone, and 3 years later you buy another smartphone, you expect your new phone to be better than the old phone, right? You don't buy the same thing 3 years later. So what this means and that's what I mean by function. It actually does certain functions very well, whether it's communicating, internet browsing, or taking pictures, whatever the function is. You have to make sure that the ability to perform the same task should improve over generations. Okay, and you also have to say that, let's say the performance doubles, but the cost cannot double. The cost to build the next generation system should remain roughly the same over different generations. That's a very tall order, meaning you have to not only jam the transistors twice as many onto a chip and make sure that it's working twice as much, but you got to do it at the same cost. Okay, because if the cost of your system starts to double exponentially, very soon nobody can afford anything, because the exponential function is very, very fast. Okay, the scalability actually requires that it's not just about the numbers, it's about the same function, improving performance, and delivered at the same cost. All of those economic factors have to be considered to really think about scalability. So for quantum computing technologies today, this could mean that when you do your class, so in quantum computers, you have these qubits, and then you control your qubits with a classical controller, whether it's a optical beam in a trapped ion or neutral atom system, or a microwave source in a superconducting qubit. You have classical fields that are controlling your qubit. And therefore, the classical controllers, when they come in and actually start controlling your qubit, that interface between quantum data and classical controller must be expandable. Okay, if you can't really jam more qubits and jam more controllers together, and at some point that scalability will break down from a functional point of view. The qubit performance, meaning the fidelity to do your preparation, logic gate, and measurement, they must enable you to run larger and larger circuits. Okay, let's say I build a 10 qubit quantum computer and then a 20 qubit quantum computer. With a 20 qubit quantum computer, I have to be able to run deeper and larger circuits because that's what the functionality of a quantum computer is. Okay, if I have 10, 20, 30, 50, 100, and if the size of the circuit I can run is exactly the same, say limited by the gate fidelities, then your quantum computer's function is actually not improving. Okay, so that's the challenge. You have to build a larger quantum system with better performance at the component level. Okay, so that's the requirement to really build a scalable system. And then the architecture must accommodate algorithm structures, meaning the way qubits are connected has to actually support these interesting and useful functions of your system. So these are some of the things that when you think about scalability, we just think about numbers in most cases. But at the end of the day, if you want your quantum computers to do better and more interesting things, all of these system level factors has to be considered as well. Okay. All right. So there are, in my mind, two different types of philosophical approach of how I'm going to build a qubit. First approach is you pick a great qubit approach. Okay. In this case, I'm going to pick my qubit to be what is like a best qubit possible. Okay. And then an example is like individual atom or atomic ion. This is, it turns out to be a very good qubit. I'm going to come back and talk about that. They're very good because the qubits are inherently identical and their coherence and the quantum properties are actually very, very strong. But the performance usually is limited by the ability to control these qubits that drive the gates. And then usually in this case, the integration and manufacturing path is less certain. And therefore, a lot of the effort should focus on the technology innovation to build better and more complex systems. Because these are great qubits, but technology to build a very complicated and sophisticated system has actually not been invented yet. Now, the other approach is I'm going to pick great technology. When I go into a semiconductor fab that makes that very complex chip processors, you very immediately think, yeah, I can actually jam a lot of different components together onto a very small area on a chip. And I can do that with, I can print like as many, huge numbers of billions of transistors on a square inch of area. So this is kind of where the solid state qubit approach is. The technology to manufacture qubits and circuits are very mature, but the performance is limited by the qubits that you can actually make using this technology. The scaling the interface between the qubits and control remains a challenge. And there's a lot of effort that is focused on improving qubit performance. How do I make a superconducting qubit and make the coherence time longer? Those actually tend to be the main focus of research. So either of this approach, I think there are two different approaches that are competing. They both have challenges. And if you look at the early days of transistor, this is actually the very first transistor that was invented at Bell Labs in 1947. And this looks like nothing like the transistors we see today. Okay, so there is a piece of germanium. They have a little insulator that looks like a triangle. They actually put a strip of gold wire across that across that sharp junction. They took a razor blade and created a little gap, and they jammed these wires into the piece of germanium to really create a transistor amplifier. Okay, and this thing up here, that literally is paperclip. Okay, that's how the first transistors were built. And this actually is a picture of the first integrated circuits in 1958. And of course, the people who invented these, maybe 1959, Jack Kilby won the Nobel Prize, and Robert Noyce, who was one of the founders at Intel. They actually came up with an idea of putting all of the functionality that is required to drive a digital circuit onto a single substrate. Okay, so although this looks very, ugly and mundane, today's CMOS technology, the integrated circuits technology, basically make our chips in basically the same way that was invented here. That's an approach that scales. Okay, so you can see that in the early days, when transistors was first implemented, that certainly was not necessarily leveraging the most outstanding manufacturing technology of the day. Actually, the most outstanding manufacturing technology of the day were vacuum tubes. Okay, because vacuum tubes were used in telephone networks, and people were building millions of vacuum tubes a year. highly scalable manufacturing technology. That's why the first digital computers were built with vacuum tubes. But they were not the best information carriers for digital information. And really, until we really invented CMOS, the complementary metal oxide semiconductor transistors, we really did not have a scalable way to build computer chips. So in this case, I would say CMOS is really kind of the best device to represent the binary bit. And once that was invented, we invented the technology to scale it. Okay, that's as you can see, I'm really picking the first approach because I think that's how all great technology have been made. Okay, but having said that, and that's my bias, having said that, the challenges that are common to all platforms is quantum computer is much more than collection of qubits, just as classical computer is much more than a collection of transistors. Okay, it's all about the function of what you can do with the machine. And therefore, the system scale design and way to scale it is going to be extremely critical. All right, any questions on this preamble? All right, the next topic, I'm going to get to the basics of trapped ion qubits. Make sure I keep track of time. Trapped ions means I'm going to start with an atom, but I'm going to strip one electron out so that the atom is actually charged. So it's an atomic ion, a single atom with one electron stripped. The reason we do that is once the atom is charged, you can use that charge as a handle to really hold on to the atom and localize its space. Okay. All right. So in order to do that, and it turns out that after you strip an electron out, I want this atom to look very much like a hydrogen atom, only one electron circling around. Then it becomes very easy to manipulate that state. Okay. If you have a lot of different electrons on the periphery, then it becomes very complex to deal with it. So what that means is I want an atom with only 2 electrons on the outer shell, so that once I strip one out, I have one left. Okay. Very naturally, that means I'm talking about alkali atoms. Alkali earth atoms, which is the second column. So these are the atoms where the last S shell is filled with 2 electrons. So once I strip an electron out, I have one left. And that's very popular system. Beryllium, magnesium, calcium, and strontium, and barium. These are all very popular qubits people use for trapped ions. There's one here where this actually means that not only this S shell is filled, but the next shell, a P shell, is completely filled. And that's this: zinc, cadmium, and mercury. These are also popular ions. And then there's a terbium out here. This is an odd one, but this one also has a property where if you the D shells are mostly filled on this lanthanide column. So there's only like a handful, maybe about 10 atoms that are good candidates for doing atomic physics with trapped ions. Okay. Yeah, I mean, people can use radium too, but it's radioactive. And I haven't seen anybody doing trapped ions with radium so far. And it's pretty heavy too.
The next one is after
this one?
Yeah.
Yeah, I haven't seen that either. I'm not sure how stable those atoms are. All right. So anyways, these are very popular. And also the other challenge is then once you strip an electron out, unlike these alkali atoms, which is naturally one electron on the outside, once you strip an electron out, the binding energy of that electron is pretty steep, and therefore you need some very short wavelength laser. So the other challenge is the laser technology. A lot of these, like beryllium, magnesium, and so on, requires very, very short wavelength UV lasers, and that's sometimes very difficult to do. So the popular ones that people use a lot are calcium, strontium, barium, and terbium. Because these can actually be accessed by mostly diode laser, semiconductor laser technology today. Okay, so it's very easy to set up these experiments. My joke is that it's not that hard, so even I can do it. Okay. All right, so those are the candidates. And today I'm going to talk a lot about this terbium ions. That's the ion of choice that we have been working with for the last 15 or so years. But there's a lot of interest in barium. And also strontium and calcium as well. All right, so now I mentioned that these atoms are now charged particles, and the question is, how do I confine it in space? Because if the atom is like running around, it's very hard to do experiments much less quantum computing. So we actually have to trap it. We have to hold it in space. And it turns out that if you have a net charge particle, and if you really want to hold it in free space, you want the electric field to be confining in all directions, right? But it turns out that there is this Earnshaw's principle. We know that the divergence of E when there's no charge is 0, which means that electric field, when it comes out into free space, at some point it has to go out. Because when you create a volume, the net electric field going in and out has to be 0 unless you have a charge in that space. So it turns out that it's hard to create a electromagnetic field where with a static field we can actually control, we can actually confine a charge. Okay, so that's actually not possible, it turns out. So what that means is when you have electric field that is confining, meaning coming into confining the charge in one direction, in some other direction the field has to go out. Meaning in this example, if it's confining in this direction, in the z direction, then in x and y direction it is going to leave. Okay, so that the divergence of this electric field profile has to be 0. Meaning if some of these are plus, at least one of them has to be minus. Okay, the coefficients. All right, so that means with a static field, unfortunately, we cannot trap an ion in free space. It's very unfortunate. But people are creative, and there are two different types of traps. One is called a penning trap, and this is where use a magnetic field and use Lorentz force to actually confine the atoms in the other axis. For example, in the XY plane where the atoms want to leave, you actually circulate it. You induce a Lorentz force with a magnetic field, and then the atom actually gets trapped because it has to circulate. So these penning traps are usually looks like a pancake, meaning atoms are trapped in one plate, and they tend to rotate. Okay, with this Lorentz force, and that's used for doing like a vacuum gauge and things like that. So it's practically very helpful. The other one is actually you now, instead of using a magnetic field, I'm going to use a time-dependent electric field, okay, which is called an RF Paul trap. And Wolfgang Paul and Hans Damelt won the Nobel Prize in Physics for inventing this trapping technology. And this is very widely used today in ion mass spectroscopy. It's technologically very, very relevant, but it's also a very popular method of choice for building trapped ion quantum computers. Okay, so what does that mean? So now I can think of this as the trapping potential. So if I put an atom in a field, and let's say I'm confining it in x direction, okay? But I have to now let it leave in y direction. So think of like a saddle point. A saddle point potential is something you can make. Saddle point means I'm confining in this direction, but I'm not confining in the other direction. And if you put an atom in here, a charged particle, it's going to be confining in this direction, but it wants to actually escape in that direction. Okay. Then what you do is instead of doing that as a static field, I turn it into an RF field. Meaning I'm going to actually flap this. Okay, so in one time frame, it's confining in this direction and escaping in this. But a little bit of time later, I'm going to turn it to confining in this direction and escaping in that direction. And if I do that flapping really fast, much faster than the atom has time to actually respond to that field, then it will actually start to feel the time average field. And now it can actually feel a trapping potential in all x, y, and y directions. Okay, and that is the principle of this RF Paul trap. Let me see if I can show you a simple example of that. Okay, so the way we do that is you think about 4 rods. So you have 4 wires, okay, and they actually form the cross section of which is arranged in a square like this. Okay, what I do is I'm going to ground 2 of these, and then I'm going to apply RF potential on the other. And then what happens is in the first time frame, when the RF is say negative, the electric field goes like this. So it will be confining in this plus 45-degree direction, but it will be escaping in the minus 45-degree direction. So the atom will now try to escape through this axis. But in the next time frame, the electric field is reversed, meaning now it's actually confining in this direction, and it wants to escape in that direction. And if you do this really fast, much faster than the atom can respond, then the atom will see a trapping potential and will tend to stay right in the middle here. Okay. And in this 4-rod trap, that means now I have a linear potential in the center along a line where the ions can be trapped. Okay. Now, of course, it's a linear, there's a translational symmetry. So I have to now put some end caps to confine that. And what I do is I take this ground, remember these are the RF voltages, but I can put some DC voltages here and ground this at DC, but apply positive biases here. That will actually make a quadratic potential along the axial direction. And with the static field in the Z direction and the RF field in the XY plane, now I can confine the atom in 3 dimensions. Okay, so that's the principle of a field. So in the old days here like 20 years ago, most of the traps were built this way. And these are like wires that are hand assembled and so on. But about 20 years ago, the community realized that if I have a trap structure like this, so that's the cross section that we're looking at, I can actually conformally map this and put all the electrodes on a surface. Okay, so let's see if you like this movie. Does the movie play? Oops. Let me see if I can play this movie for you. What you do is you start, and these are the RF fields, these are the DC fields. And I'm going to conceptually just split this DC into 2, and I'm going to move it, conformally map it, and then put it down here. So now, compared to the original plan, I have a ground plane here, RF and ground, so that 3-dimensional square has now been actually flattened onto a surface. It turns out that this conformal mapping works. And then what the nice thing about that is now you can actually fabricate these trap electrodes on a surface using, say, a silicon fabrication process. Okay. When you do that, then the ions actually float just above the surface. It's kind of the typical distance of that from the RF ground to the trap is basically the distance from the center of this rectangle or the square to one of the electrodes. Okay, roughly the same. So by designing the dimensions of these things, you can control this height. And typically we use something like 50 to 100 microns is a typical structure, which means that the dimensions of these electrodes are typically in tens of microns. So they're not very, very hard to make. But you can actually make them very reliably. So, and that actually was one of the very first contributions that I made to the field, is to really think about making these traps out of semiconductor fabrication processes. So as you can see, that there is a trapping potential that forms if you have RF electrodes and ground planes somewhere else. And you can actually fabricate this whole trap structure on a chip. All right.
How do you determine the RF frequency of the trap?
Yeah, so the RF frequency, that's a good question. So if you look at this RF Paul trap, there are what we call the trap maker's equations. Okay, so it's a combination of a few things. First, there is the charge to mass ratio. So each atom has 1 electron charge, and the atom, based on which one you pick, has different mass. So that charge to mass ratio actually has a stability parameter in this trap. And that's how we build mass spectroscopy, is you ionize some of the molecules and then you put it through here. It's going to confine certain charge to mass ratio, but make it unstable and push everything out. So you can actually select that. So there is a stability condition, which depends on the charge to mass ratio, and then the distance. And then you also have the RF frequency and the RF amplitude. And you want to make sure that the RF frequency is fast compared to the response time of the atoms, which is the secular frequency. So yeah, there are probably like a handful of equations that describes exactly what the parameters are and how to design that. But I'm not gonna get into details of that here.
It falls onto the megahertz range, or
yeah. So usually for the terbium that we do, what happened here? Do we know what just happened? 예, 그러면 이렇게 할게요. 잠시만요. 랩톱에서 그게 빠지네. 잠깐만요. 이게 지금 제 컴퓨터 스크린을 모니터하는 거라서. 네. 이 정도로 해보죠. 예, 그래서 티피컬하게는 저희가 이거를 아까 말씀드렸지 이 디멘션을 한 100마이크론 정도로 잡으면 이터비움의 charge to mass ratio의 경우에는 RF 필드의 프리퀀시는 30에서 50MHz 정도 되고 그다음에 그 trap potential, trap 프리퀀시는 한 a few megahertz. 비율은 10대 1 정도 됩니다.
So hypothetically, you could trap a bare electron.
Yeah, you can actually trap bare electrons, and there are some experiments going on, but there the charge to mass ratio is really, really, really small. So you need a very different dimensions. You probably have to have, I haven't done the numbers, but basically your charge is the same, mass is 2,000 times smaller, so your frequency has to be that much higher, and so on and so forth. Okay. So I'm going to actually then think about what types of atomic qubits there are. Okay, so usually you want two levels in an atom, and one option is you start from a ground state. Let's say in a trapped ion remember there's one electron that's in the valence shell, and that's called an S state, and you have either spin up or spin down. So there's a ground state, and then you can actually put it up here into the P state. But the problem with P state is it's the decay from P to S is allowed by dipole transition, meaning after just a few tens of nanoseconds, it will just decay. Okay, so it actually scatters photons very well, but it's not a very good qubit because you can't keep it there for a while. Now, the D states, however, is actually only allowed by quadruple transition, and therefore the decay rate from here to here can be very slow, depending on the energy of this. So for example, in calcium, this is about 1 second, meaning if you put this qubit electron up here, it will stay up there for about a second before it decays. So you can use that as a qubit, meaning S is your spin down state, your 0 state, and your D is your spin up state or 1 state. And then this qubit can be maintained for about a second. If you go to barium, this can actually get up to about 30 to 80 seconds, depending on which one to use. If you go to other atoms, you can actually come down to milliseconds. So depending on the atomic qubit, atomic species of choice, this S to D level can be used as a reasonably good qubit. But the challenge is the frequency difference between these two levels are in the optical frequencies, 10 to the 15 hertz. And you have to drive this by a very carefully tuned laser beam. And the frequency of that laser beam has to be very stable. In order to get to a second, your frequency also has to be like 1 hertz line width. Right, at the carrier frequency of 100 terahertz. So those are technologically very challenging, but I think it could be done. Yes. Yes. So in most cases, both S states and D states have multiple degeneracies, and they're usually lifted by applying a small magnetic field. So you actually typically pick a sublevel in S and a sublevel in D and use that as your qubit.
I think they couple with the same spins.
No, these are not actually electron spin. These are just if you think about a two-level system, we can describe it as spin. So just think of this as your 0 state, and that is your 1 state. It's not an electron spin of that. Yeah. So again, all of these have sublevels that are split by various couplings. All right. The other option is to you look at this hyperfine qubit. Hyperfine transition means if your nuclear spin is non-zero, then the electron spin of this ground state and the nuclear spin of your nucleus can actually interact. And that interaction is called a hyperfine interaction. And the most famous one there is actually the hyperfine interaction in a hydrogen atom. Okay, and that hydrogen atom, this frequency is 1.2 gigahertz, very famous. And because the nuclear spin remains so well isolated from the rest of the universe, even inside your body, we can actually drive these nuclear spins to line up coherently. And then we can keep that coherence for a while, meaning like for seconds, okay, if you polarize it. And that is precisely how MRI is done. Magnetic field resonance. Your body has lots of water. Every water molecule has 2 hydrogen, and every hydrogen has a spin half nuclear spin. So in an NMR, they will actually magnetize all of the all of the nuclear spin in your water molecules in your body. They line it up, and then the spin starts to precess, and they use that to do medical imaging in your body. Okay, so even in a human body, this nuclear spin can remain coherent, which is pretty remarkable. Okay, and that's used as a technology. That's how well isolated these nuclear spins are from the rest of the world. And therefore, if you look at this, right, the decay time for this is actually a magnetically induced dipole transition, and this frequency is only on the order of a few gigahertz. Then it turns out that for hydrogen atom, this decay time, does anybody know what the spontaneous decay time of a hydrogen ground state is? Anybody care to guess? Nobody has measured it, but people have computed, because it's about 3 million years. Okay, so this nuclear spin, they're extremely coherent. Okay, so we like to use this qubit because the zeros and ones, they never spontaneously flip. It will take thousands of years. Well, but you can drive it with a microwave field. Yeah, but spontaneous coupling is very weak. So you have to drive it with a very strong field.
Then in order to make use of as a qubit, you have to make it couple somehow
to the external field. Yeah, but spontaneous, meaning that's driven by this vacuum fluctuations, is nothing.
But then low coherence time comes from the vacuum state.
That's right. So if you look at Wigner-Weisskopf spontaneous emission theory, the transition is a function of dipole moment and your frequency, right? And then a bunch of just other factors. If it's a magnetic dipole transition, then it's actually very is lower than electric dipole transition by, I think, 8 orders of magnitude or something. And then there is the frequency. So compared to this optical transition, and it goes as the 1/3 power of the frequency. So it turns out that the magnetic field, microwave frequency regime and magnetic dipole transition, the spontaneous emission lifetime is really long. Okay, nobody has the patience or lifespan to actually measure them. All right, so that actually comes to my question. I said I like these atomic qubits because they're really, really good qubits. Okay, so let's think about if you're looking for a perfect qubit, what does a perfect qubit mean? What is a good criteria for defining like a really, really good qubit? And of course, companies like Microsoft is looking for a perfect qubit by looking for topological qubits and all these complex things. But I think the fundamental physics is a lot simpler than that. Okay, and this is why. First of all, what is the criteria for defining a perfect qubit? So there is the T1 and T2. Again, this is kind of in the nuclear NMR terms. T1 is if you put your qubit in a one state, the higher energy state, what is the time scale over which that decays into a lower energy level state? That's your T1. Okay. T2 is if you put a superposition of 0 and 1, there is a phase. The phase is actually defined if you have an energy difference in quantum mechanics, there is a trivial rotation of e to the I omega t. It starts evolving based on what that energy difference is. So there's always that time evolution. But if that frequency is super stable, then you can predict exactly what the phase is. But if that frequency starts to fluctuate, then as you integrate that rotation over time, you start to lose control of exactly what phase you're looking for. Okay, so the phase stability is actually related to how stable that energy difference actually is. Okay, so that the time scale over which that phase coherence is lost is called T2. And these two are related because if your energy level decays, that means I have a little bit of uncertainty in your energy level, because if it decays, that means your energy has a finite width, which means that I have finite uncertainty in the frequency, And that finite uncertainty in the frequency will translate to phase loss. So there is a relationship between the best case T1 and T2. I think T2 is like 1/2 of T1 is a fundamental relationship. Okay. Now it turns out that if you have a hyperfine qubit, as I said earlier, for hyperfine ground state of hydrogen, this spontaneous emission transition rate is about 2.9 times 10 to the minus 15 per second, which actually is 1 decay per 11 million years. I misspoke, I said 3 million, but this is about 11 million years. Okay. And between hydrogen, which is 1.2 gigahertz, to the ytterbium, which is about 12 gigahertz, is 10 times longer, higher energy, which means that decay is 1,000 times faster. So for ytterbium, it's probably about 10,000 years, several thousand years. Okay, so it's really long. So you don't care about this. Your spontaneous emission is never your fundamental issue. It is actually limited by technology. Meaning, if your vacuum is not perfect, then you have a qubit and some background molecule will come in and collide. And when that collides, then it gets screwed up. Okay, so your coherence time T1 is not limited by fundamental physics, but is limited by technology, your vacuum levels. All right, so that's T1. For T2, as I said, if you have a qubit of 0 and 1, that's described by this theta and phi. This theta is the relative weight between 0 and 1, and that exactly changes if there's a spontaneous emission. But this one, the phase, this changes if you lose track of what this omega is. But as I said, this is the one where your omega, the line width of this, is as small as you can think of. It turns out that it is such a fundamentally stable thing that we actually decided to define 1 second, or the absolute frequency reference, by using the hyperfine frequency of a cesium atom. Okay, so the cesium has a hyperfine splitting, and that's 9.192631770 gigahertz. And this number is exact. It's not an approximation. We just define the absolute reference of time based on this piece of physics, because that's the most stable thing, at least in the 1970s, that we could think of. That's not hard to measure. So what this means is if I use the cesium's hyperfine ground state, by definition, my frequency is exact, meaning this will never dephase, by definition. Okay, so what happens is in reality, I need a clock. I need a laboratory. I have to measure time, right? So what I do is I create a microwave oscillator that has you have a 1 gigahertz reference clock, right? That reference clock actually has to be locked to this thing because this is the absolute truth. If you can lock your experimental clock perfectly to this qubit, then this will not dephase. Okay, but your ability to tie your classical clock to this absolute reference is your technology. That's your atomic clock technology. And that typically limits your coherence time in your system. So in this hyperfine qubits, if you can actually make better control, technology improves, then the coherence time improves. And in fact, for ytterbium ions, when we trap, we get about a second coherence time. But people have taken the same physical systems, and this is actually Professor Kyuhan Kim at Tsinghua University, spent a lot of time, same qubit, improving technology, improving oscillator, do better magnetic field shielding, do better isolation. And he could actually extend it to about 1.5 hours. Same physics, only limited by technology. Okay, so this is really nice. This is really nice, meaning if you have a hyperfine ground state of an atom, then your T1 and T2 are infinity. You're only limited by technology and not by any fundamental physics. Okay, this means that you put a qubit, store a qubit in atomic physics, these are hyperfine qubits, and they, if you can isolate them perfectly, will stay there forever. Okay, now that does not mean that you can build a perfect quantum computer, because when you start to manipulate that and run gates, then that's when error comes in. But all of that error, again, is limited by the technology of your controller. Okay, so here I have a really good qubit, and the performance of my computer will improve with being smart about how to improve your technology. And that's actually very different than trying to come up with a new piece of physics or discover new physics. Okay, all right. So I'll move on and talk about the hyperfine qubit. And this is ytterbium 171. It actually happens to have a nuclear spin of 1/2. So you have, if you go to the ground state, the electron has spin 1/2, spin up and down. nuclear spin is spin up and down. So when you interact these two, there are 4 states. And that 4 states splits into a triplet and a singlet. And if you look at these middle 2 states, that frequency is really stable. Okay. If you actually go to 0 magnetic field and isolate everything, this is just as stable as cesium. And you could have picked this one as your absolute frequency just as well. Okay. And that's what people do. People actually build atomic clocks with this type of fine states as well. Okay. It's a good piece of physics, very stable field. And you can get, as I said, about a second without trying very much. This slide is old, so I said your T2 can be 15 minutes, but with Professor Kyo-Han Kim's work, he's actually extended to about 90 minutes. Okay, so you can make it really long, like 1,000 times improvement in T2 and things like that. It's all about doing better technology. Now, when you want to start to manipulate these things, I actually am missing a slide, so I'm just going to explain by words. Initially, if you don't know what the state is, the electron can actually stay in any one of these 4 states, and you don't know what it is, and you want to initialize that qubit to 0 state so they can use it. So what you do is you shine a laser beam that is resonant with these 3 levels. Now, we put a small magnetic field to split these 3 levels, but the energy separation here is actually narrower than the transition line width, so they actually are blurred, right? We don't apply a big field, we apply a very small field. And what you do is you drive a transition between these 3 levels and those 3 levels up here. Okay, what this means is if your electron is here, it stays there. If your electron is in any one of these states, it gets excited, and then it spontaneously decays. And it can decay from these 3 states into one of these 4 states. If it happens to fall in here, you don't touch it anymore. If it falls back to one of these, then you pump it again. And then with some finite probability, it falls down here. Anything that actually remains here, you pump it again. So after scattering many, many, many photons, and it happens with about 1/3 probability, it will come back down here. So if you take that 2/3 probability coming back down here and raise it to like the 100th power, then you basically get to 0 very quickly. Meaning you can actually take all the population here, after scattering about 100 photons, all of the electrons here will now be pumped into this. And that's called optical pumping. And you can actually do this in this example. You can do that with about 6 nines of fidelity. So initialization error, fundamentally, is about 6 nines. Okay, that's what you can do. Now, of course, that's hard to measure because our measurement fidelity is worse than that. But you can do a very, very efficient initialization using optical pumping. Now, when you do a state detection, what you want to do is I want to differentiate between this one and that one. So what you do is you now shine a laser beam that's resonant between this and that state. And then you excite it from here to here, this one. Okay. Now, this one can only decay back into these 3 states, and it does not decay into that one. And the reason is this is a atomically forbidden transition. Okay. So what happens is if you start it from here, it actually goes back into one of these 3 states, and then it gets pumped again, and then it comes back down, and it keeps cycling. What this means is the atom continues to scatter photons, and when you shine a laser beam, it glows. So what you do is now I'm going to collect the photons from the atom and put it into a high efficiency detector, and I get a distribution like this. It's a Poisson distribution, but it does mean that the atom is scattering photons. Okay. Whereas if you start from here, this laser beam that you're using to drive it from here to there is actually completely off resonant. And therefore, the atoms don't scatter any photons. So your statistics look like this. You get 0 photons. And you can actually tell this kind of distribution, atoms glowing, to that kind of distribution where our atom remains dark. You can discriminate these 2 really well. Okay? And we can typically do that with about 3 nines of fidelity. And there are other techniques where you can actually do this with better. So 4 nines, people trying to reach 5 nines and so on. So detection fidelity is also very high. All right. The next is I want to do a single cubic gate. Single cubic gate means I want to manipulate my population between these 2 states to create superposition states and whatnot. And here I show an example of what's called the Rabi oscillations, which is I prepare this here, and then I shine some microwave that's resonant with this, and this will actually move the population to here, meaning that now it actually becomes, everything comes up here, and it comes back down, it goes up here and comes back down, and it keeps oscillating. And by controlling the time and the phase of this microwave, you can actually drive arbitrary single qubit transitions. Now, at Oxford University, they actually can do that with an error of 10 to minus 6. But it's very easy to do this with an error of 10 to minus 4. Yeah, that's very easy to do. So microwave gates are very nice, but there is a downside. If you have a bunch of atoms that are confined in a very small space, the microwave has a very long wavelength. So it's very hard to target one atom and flip it, leaving everything else intact. So what we do is we use what's called a Raman transition. And in this case, what I do is I take two laser beams whose frequency difference is exactly this energy difference, 12.6 gigahertz. So I drive with two laser beams. And then I make sure that this laser beam excites this electron to appear and not actually hit one of these resonances, which means I'll go virtually get excited, and then it only goes virtually up here, and then it immediately gets stimulated emitted down here. Okay? So what that means is using two laser beams with a frequency difference, the combination of these two laser beams will act exactly like a microwave field to this atom. And the benefit is you can actually tightly focus the laser beam and address one atom at a time. Okay, so this coherent coupling rate, which is a good one, which is given by basically the electric field strength product of the two electric field strength of the lasers, divided by this detuning, which is how far you separate this virtual level from here. So that's a good thing. And then the bad thing is actually spontaneous emission. It will still be able to virtually and then scatter down and lose coherence. But by increasing the detuning, you can actually make sure that the coherence can improve while the spontaneous emission remains small. Okay, so you want to make sure that this detuning is very large. Okay, so that's a small piece of physics. But you can see that you can typically create this ratio, spontaneous emission error rate, down to about 10 to the minus 6 in this ytterbium system. Okay, the next question is how do we do 2 qubit gates? I'm going to actually use this as an example of how we're going to do 2 qubit gates. So now I'm going to think about a chain of atoms. These are ions that are separated by a few megahertz, a few microns. So what I do is I create a big trap and put in a whole bunch of atoms. And then they push each other and form this crystal. But then I also cool down the motion by laser cooling and make sure that this atomic chain goes down to its ground state. So it's not moving at all. And then what you do is I bring in 2 laser beams. Okay, I bring in 2 laser beams. And I control the laser beams in a way that if your electron was in the ground state, in the 0 state, then you push the atom down. Okay, but if the electron was in the 1 state, I push the atom up. Okay, and that's what we call a spin-dependent force, which we can actually apply. So what this means is if the atom actually had a superposition of 0 and 1, when you shine this laser beam, the atom will actually split. Okay, part of the atom will move up, the other part will move down. 공간적으로, yeah, in space. Okay, it looks very strange, but you can do that. Okay, all right. So think about a case where if your electron was in 0 state, it moves up. If the electron was in 1 state, it moves down. Okay, I'm going to push this up. I'm going to push that down. All right. So what I do is I pick 2 atoms and I want to create a gate. So what I do is, the ions are separated by R, which is a distance of about 5 microns. This delta, the space by which I split this out, is about 10 nanometers. It's a few nanometers. So the ratio of this is about 1,000 to 1. Okay, maybe 500 to 1, but it's actually quite small. Then what I think about is the energy difference between the 2 states. Now, if the 2 electrons are up here, and if I push them both up, then the separation really hasn't changed. Okay. If they were like this and I push both of them down, then the separation hasn't changed. But if they started like this, and if I do this, then the actual distance between these 2 actually is now bigger by this square root of R squared plus delta squared. Okay, and if I look at the energy difference between these 2, that actually looks like a dipole-dipole interaction. So now there's some energy difference when the 2 atoms are in the opposite state. Okay. So what does that mean? Now, if I actually then maintain that energy difference for some time, remember energy difference actually leads to frequency difference. And now I can actually spin it a little bit. And if I control this time such that this phase shift is pi over 2, then I have a gate that looks like this. Meaning if this were down, down, no phase shift. If this up, up, no phase shift. But if it's up, down, and down, up, then I actually induce some phase shift here. Okay, so now I collect some phase shift if the two qubits are in the opposite state. But this phase shift is exactly the same. And that actually makes this an entangling gate. Okay, now that entangling gate looks like this. It looks like a product of the two X operator, Pauli operators, if you know what that is. And this is what we call an Ising gate. Okay. Now it turns out that you can actually do this gate in a few maybe 100 microseconds, and your fidelity can be pretty high. Okay. And the nice thing about that is you can actually pick arbitrary pairs of qubits in the system, and then actually apply that gate in the chain. Well, it turns out that it's an X, but it's just a rotation of basis. Okay. All right. So sometimes this is an extension of what's called the Momo-Sorensen gate. But the nice thing about this is you can actually pick any pair and do your gate. Now, in reality, it's actually a little bit more complicated than that, because once you actually move the atom up, kick it up, then all these motion, because of the Coulomb interaction, all the motional modes are coupled, and all the chain starts to move. Okay, all the chains start to shake. So you actually have to control that force in a very careful way, so that at the end of the gate, the entire chain comes completely to still. Because if there is any residual coupling between your spin and your motion, or your qubit and your motion, then that leads to errors. Yes. Yeah, so that's exactly what I said. Because the two electrons that are not chosen, the qubits, it will actually interact with everything else too. So you actually have to do this control loop. It's a pure classical control to actually make sure that everything else is suppressed, and only this phase accumulates between those two qubits. And that can be done. Okay, so that's how we make these long chains work. Okay, so at the end of the day, if you look at this, these are some of the error sources that are computed for this case. So still spontaneous emission dominates, but we feel like we can actually make gates that have up to about 3 nines of fidelity using this physical mechanism. Okay, in a terbium system. All right, so this actually is a long history of the 2 qubit gate error in 3 different physical systems. So in trapped ions, they've actually always led the way, and we actually now have some gates that are better than 99.9% as of 2021. The superconducting qubits actually started out, and we're getting about 99.5% qubit errors. I don't know if there's another data point down here. And then the neutral atoms are starting to improve. Their gate fidelity is starting to improve. But you can see that as a function of time, right? There's about 7 or 8 years difference between these 3 curves, right? So although these technologies are really doing well, the trapped ion, at least at the component level, have been doing really well for a long time. Okay, so the reason, the way we think about the spam is some of these data with, I think there are some stars here. I think even in the trapped ions, when you really get down to this kind of levels, you have to subtract spam. Remember, the spam errors in trapped ions is about 0.1%. So if your gate errors are much smaller, you have to somehow either do randomized benchmarking, some technique to take out spam. The spam errors in these systems tend to be quite a bit higher. So you really cannot measure better than 99% because spam error dominates. So of course, once your trapped ions comes down here, you actually have to subtract the spam so it doesn't dominate. Okay, so this is actually some of the recent work that I have done. In the original proposal for doing a control NOT gate, it's called the Sirac-Zoller gate. This was the very first paper. And that actually uses not only the qubit state, but one extra state, but it actually also requires that these other states remain extremely stable. But if you do that, then you can actually use the the three levels in the atom and the motional degrees of freedom to create a control NOT gates, like multiple control NOT gates. Okay, it was actually remarkable. This was in the original paper, and people have done these gates, but these Momo Sorensen or the XX gates were performed so much better that everybody moved into that for the next, I don't know, 25 years or so. But very recently, this was actually very recent work in my lab. We actually started to look at control NOT gates, control NOT gates. So we could do a 3-qubit Toffoli, 4-qubit Toffoli, and 5-qubit Toffoli gates. And we were able to get some pretty reasonable performance out of it. But in order to do that, you actually had to improve our experimental setup and so on. Okay, so that's not so although the XX gate, the Momo Sorensen gate was the most popular, it is actually not pretty interesting that we can actually come back to some of these more advanced gates more recently. All right, so just before we go to a break, the really nice thing about this from an architecture point of view is if your qubits are in a linear chain, and if you can pick arbitrary pairs of qubits, your qubits in this graph are all-to-all connected, meaning you can pick arbitrary pair and do a direct 2-qubit gates. It turns out that if you control them really well, you can make sure that all of these gates that you do here have almost the same fidelity and takes almost the same time. Okay, so you can actually engineer the system so that the quality of all of these gates are extremely uniform. Whereas if you have qubits with wires, and these are the ways that in a superconducting qubit, for example, you actually have to create a wire, a microwave resonator to couple the 2 qubits, and you have to print in the wire. And if you don't have a wire connecting 2 qubits, you cannot apply a direct 2-qubit gate. For example, if you wanted to take this qubit and that qubit, I want to do a 2-qubit gate, then you actually have to translate that to a whole bunch of 2-qubit gates. And from an algorithm execution point of view, that actually increases the number of 2-qubit gates, and your gate fidelity is not perfect, and therefore the performance of the circuit will tend to degrade. So this is kind of the architecture where if you have a fully connected qubit, you can actually run circuits and gates more effectively. All right, so maybe with that, I'd like to take a little break, and maybe we take about a 10-minute break. And then in the second half, I'll talk about some of the state of the art and what we're able to do with them. Okay? All right. 자, 그러면 이제 지금 기본적으로 원래 말씀드렸으니까 이제 시스템을 어떻게 만드는지 이제 세컨 half는 기어 시프트라 가지고 피직스 강의에서 엔지니어링 강의로 넘어가다. 또 이제 아까 말씀드렸지만 그 라만 빔을 가지고 레이저를 컨트롤하려면 이제 이런 스케매틱하게는 우리가 레이저 빔 하나를 시작해 가지고 이거를 쪼갭니다. 쪼개서 이 레이저 빔을 아까 원자 체인 하나하나에 켜줄 수 있게 이렇게 옵티컬 시스템을 만든 다음에 이 양자 서킷이 여기 있으면은 일단은 그 옵티컬 펌핑을 통해서 모든 큐빗을 0이란 상태로 이니셜라이즈 시켜주고 그 다음에 이제 게이트를 할 때는 아까 말씀드린 레이저 빔을 우리가 원하는 대로 프로그래밍을 통해서 조절을 해가지고 싱글 큐빗 게이트, 2-qubit 게이트 뭐 이런 것들, 또 어떨 때는 멀티플 2-qubit 게이트 이런 것들을 우리가 그 회로에 있는 대로 그다음 그대로 프로그램을 해줍니다. 이건 전부 다 소프트웨어로 할 수 있고 그 다음에 아까 말씀드렸듯이 쿨롱 인터랙션 때문에 arbitrary pair 사이에 entangling gate 할 수가 있죠. I started speaking Korean, so I'm going to go back to English. All right, so when you're done, we shine a laser beam, and there's a state-dependent scattering, a fluorescence process. So if the qubit was in one state, they glow. If the qubit was in 0 state, they don't. And you can very quickly tell your 0 from 1. Okay, so that's how schematically how it works. The first system that was kind of semi-automatic was actually built in 2016. And this was worked by a group of in Chris Monroe's group. And of course, you know, these systems became the foundations for the quantum computers that we built at INQ. And the first author here, Shantanu, is currently works at INQ as an engineer. So here, this is the old style UHV chamber. And in this chamber, they actually had this what they call a blade trap. And this is not even a trip trap, but these traps could contain like 5 ions in the middle. And then they created this laser control system where was one big fat beam hits all the atoms, whereas they also had these individual beams that can come from the opposite side, and they can actually control turn on and off, or even turn everything on. So you can actually do an individual beam pair to drive the Raman transition. Okay, they come from the same laser. This actually shows how this multi-channel acousto-optic modulator built by Harris, now called L3 Harris. You can actually turn these individual beams on and off just by programming this with an RF source. Okay, so now we have all the tools to actually drive this. And then, if you have an algorithm, say a quantum Fourier transform or some algorithm at the user, this actually has to be translated to individual controller all the way down to the gate. So that's the mechanism it works. So first, your user thinks about this quantum Fourier transform over a 5-qubit. You draw this circuit. And then this circuit, like controlled phase rotations, now have to be translated to the native gate. Remember, this XX gate or the almost Ising gate is what we do. So now we have to translate this user-friendly gate to a machine-friendly gate. You can think of it as like an assembly process, right? So this is what the machines think of, are single qubit rotations and these XX gates. So you have to translate that circuit into what the machine likes to see. We call it the native gates. And then in order to apply this XX gates between, say, the first and the third qubit, you actually now have to control this laser pulse. Remember, when you start driving this gate, all of these 5 different modes will start to oscillate. So what you do is you have to do the control in such a way that at the end of that process, only one of the pairs actually will accumulate the phase, and all the other motion has to come to a dead still. Okay, and that's what this process is. So this is really like a control layer. This is a much lower layer in the control layer. And once that's all designed, then we actually apply these lasers onto the atom, and then we actually run the circuit. So this is actually a multiple layers of software control that's needed to actually translate the gates that you run or circuit that you want to run into the laser pulses that actually hit the atoms. Okay, so we actually have to build all of these tool sets. And by doing that in this early experiment, they had a 5-ion chain. There is 5 choose 2, which is 10 possible pairs of gates, and they ran all the gates. You can see that the errors are probably in the 2 to 3% range in this, without subtracting spam. Okay, in this case, that includes the spam errors, that state preparation and measurement errors. And over time, they improved that gate to about 99%. So we actually have, in 2016, they had a 5-qubit system with 99% gate fidelity. Today, we have a next version of the system, again, at Duke Quantum Center now in Chris Monroe's group. They actually have can run with about 23 qubits, with about 98.5 to 99% kind of fidelities. Okay, so we can actually do that. They can do arbitrary pairs, pairwise qubits, and so on. So all of that is actually we can actually engineer to our original liking. So this is actually a paper from Professor Margaret Martinozzi. She's actually a computer architect at Princeton, and about 4 or 5 years ago, they did some work to benchmark the performance of various quantum computers using an algorithm. This is actually algorithm-based benchmarks. And here they had 3 quantum computers from IBM that had 5 qubits, 14 qubits, and 16 qubits. They had 3 Rigetti machines. But back in 2019, we did not have a commercial quantum computer on the cloud from IonQ. So they went to University of Maryland and went back and used this system to actually characterize the operation of the circuits. So now there are these different classes. This BV is called Bernstein-Vazirani algorithms that utilize 4, 6, and 8 qubits. HS is an algorithm called hidden shift that runs, again, 2, 4, and 6 qubits. A Toffoli gate, it's a control-not gate. In order to do this, you actually have to break Toffoli gate into, I think, about 6 CNOT gates to run this. Fredkin gate, it's a control swap gate. So there are a bunch of other things in there. Quantum Fourier transform. This is a little adder, like a digital classical adder, and so on and so forth. So this is very complicated. So let me break it down for you. So first of all, there are these 6 and 8 qubit circuits where they were able to only run it on 2 IBM machines and 2 Rigetti machines. And then the ion traps, we don't have data because the ions only had 5 qubits. Okay, so 6 and 8 qubit we couldn't run. So I'm going to ignore this for now for comparison. Okay, and then there are these 2 algorithms. This HS2 is a 2 qubit hidden shift algorithm. It's an algorithm between only 2 qubits. So if you have 2 qubits and you can do a gate, then you can run this. So every system actually has that capability. So you can see that the success probability is pretty high. It also turns out that quantum Fourier transform can be efficiently implemented if you only had nearest neighbor coupling. Okay, so if you have a chain of ions that are a chain of qubits that are connected only nearest neighbor, you can run a quantum Fourier transform on that very efficiently. Okay, so it's not surprising that in QFT and HS2, all of these things actually do pretty well. The ion traps are a little bit better because their fidelity was better, but they actually work reasonably well. But then if you go to all of these other algorithms where the qubit mapping is not directly done onto only nearest neighbor qubits, then you can see that the architectures where things are not globally connected, the performance starts to go down, meaning the accuracy or the measured success rate is now somewhere between 30 to 60%. But you can see that the trapped ions, the success probability remains all very high because every qubit is connected to everything else. So this actually shows some early examples of how your architecture can really affect the performance of your qubit algorithm. Okay. All right. So that was the highlight of the architecture. I'm going to share a little bit more about how we actually build these systems physically in the lab. All right. So I mentioned that starting in about late 2000s, 2008, 2009, and 2010, people started to really take on the idea of the surface traps, meaning they're taking ion traps and try to put it on all the electrodes onto the surface so you can actually use the microfabrication techniques to make them. Okay, so there were some collaborations that we have done with Sandia National Labs and Georgia Tech Research Institute. You can see that we create all kinds of different traps that have junctions. You can actually make a circulator trap, a ring trap, a linear trap. And these traps have worked out really well. And these are the ability of what people can do. You can see that in this video, they're loading one ion at a time over here. And once an ion is loaded, they actually change the voltages on these electrodes and move this ion over here. And they're actually building up an ion chain one by one, right, to whatever length you want. You can actually do these things. And this is actually a very simple routine manipulation of ions you can do in a typical surface trap. And we very easily build ion chains of 30, 40, 50 qubits. You can do that routinely. Okay. All right. So this is actually some of the work we've done with Sandia National Labs. Where's the picture? Okay, there it is. And this was a high optical access trap that we started developing maybe about 10 years ago now. And here the idea is I'm going to have a linear chain of ions here. And this trap happens to have a little slot, meaning there's a slot in the middle of the trap. So you can actually trap an ion on top here. But we also made sure that this looks like a bow tie, okay, meaning that the width of this isthmus is fairly narrow. And that allows us to bring laser beams skimming through the surface because the laser beam actually diffracts. If this is too wide, you're going to start clipping the beam. In order to actually be able to tightly focus the beam, we actually had to make the width of this trap region very narrow. And that's what led to this bow tie shaped, what's called a high optical access trap. Now I happen to have a trap in a package. I'm going to pass it around, but I need to get it back. And this is actually a package trap. It's a small chip you can see in the middle that also has a bow tie-like shape. And it's gold coated. And right in the middle here, just in about a few tens of microns, that's where all the qubits are. That's where all the quantum computation happens in a small area that is less than a millimeter. Everything else that we build is to build the controllers to actually deliver the laser beams and do stuff there. Okay. And there's plenty of room for all of you to think about new technologies that can make that smaller. Okay, because the real quantum computer doesn't have to be much bigger than a millimeter. Okay, everything else is technology improvements. Okay. All right, so I'll pass it around. Okay, this vertical slot also allows us to really tightly focus the beam, other than the skimming, beam skimming through the surface. And then this is actually a little bit of my MEMS work where we made some these tiny micro mirrors that are about 300 microns in diameter. I think this was Diameter of this was maybe 250 microns. And I can tilt these mirrors and I can actually steer laser beams. And that allowed me to really address individual atoms in a chain. So this is a little graph where I'm actually writing Duke with steering our beams and so on. And you can actually make sure that these beams are very, very tightly focused. You can actually steer the beams in a linear chain that allows you to actually hit individual atoms on the chain. So this kind of technology is all very routine. Okay, so this is what that experiment that Chris Monroe had at the University of Maryland in 2016. Okay, a typical atomic physics lab. They have plenty of optical tables, lots of optics assembled on the table, a lot of controllers, a lot of people in the lab tweaking everything and running the experiments and so on. But it doesn't have to be this way, right? This is how people have always done it. But when you're thinking about building a computer, this doesn't look like a very reliable computer. So what we decided to do when our IARPA project started in 2016 is let's take that and then let's break them down into subsystems. Okay, so we have a vacuum chamber. Yeah, you need some vacuum chamber, and then we attach some optics around that. You need some CW lasers. These are low power lasers that are resonant that are used to do like state initialization, laser cooling, state initializations, and detection, and things like that. We need high power laser that drives all the Raman transitions and Raman gates. We need a delivery system to allow individually addressed beams, and that actually requires a pretty complex optical system, at least way back then. And then we need the trap. We need real-time software controller. So can we actually now break your system down into these various subsystems and then assemble them into a box? Okay. So that's what ended up happening. This is actually the first system that we built at Eureka, which is our IARPA-funded program. But we also took the same blueprint and built our first quantum computer at IonQ. Okay, and this one, the first generation quantum computer is not in service at IonQ. We actually built several more iterations of generations so that a company things actually evolve a lot more quickly. But this first system that we built at the University of Maryland is currently at Duke University. This one actually ran the very first quantum error correction experiment that was published in 2021. And this also right now runs about 25 qubits in a fairly routine way. So you can actually run them really well. And then this one actually has the ion trap, the bow tie trap, as we said. There's this bunch of controllers. There we go. A bunch of cables that come in, which is we program the RF pulses here, and that's going to control all the laser beams. And you can actually typically box it up. And the nice thing about it is you really don't need to be in the room. Okay, so we built this system in 2016, and by the time we were done in 2019, we had all the software that was built, so you don't actually have to sit in the room. And boom, we're hit with COVID. Okay, so nobody can come into the lab. Everybody stays home. And Chris was telling me that all of their researchers are staying home and running this quantum computer from home. And there is nobody in the lab, in the building. And they said the data can't be any better because nothing is moving. There's no temperature change. Everything is super stable. So we came to a point by 2020, 4 years later, where we have a box like this sitting in the lab. You sit at home and you run all of your programs, right? We can do that in 4 years. And of course, the IonQ's commercial quantum computers run that way. We actually run 24/7. Okay? So all of that can be engineered. All right, the other thing that we've done is, I'm an engineer by heart, I think. So this is how your typical laser optical system is built, right? If you go to an optical table, we have these individual mirrors and that are mounted, and then you have to tweak it. You have the laser, you bounce it around, do all of the modulation, and then you have to couple into a single mode fiber. The coupling is super sensitive. And every 2 or 3 days, the coupling actually drifts, and then you have to tweak it back and so on. All of that's really painful. That requires people to sit in the lab and tweak things around. So I was thinking, okay, well, can I do much better? And one of my colleagues, Dana Anderson, who is actually a founder of Cold Quanta, he said, if you know exactly what you want, you can make it really well. Okay. So that's what we did. Okay, so this one is actually nice, it's super flexible. But at the end of the day, once you have an exact optical system that you have, you never change it. You just want that to be stable. So what we did is we went from this kind of a Lego-like piece by piece assembly to a CAD-based design. okay, this is the optical function I want. I want the laser to come in through one of these fibers, or fiber N. I want it to go around. I want some of the beams to go through EOMs, others to go into AOMs, and then bounce it around. And eventually I couple it back into a fiber out, and then I want to deliver it to my system. So we actually designed this all on a CAD, and then we did a precision machining. So by that, and all of these optical mounts are actually mounted onto the plate with a dowel pin reference, which means you can position all of these components to within 25 microns of your design. Yeah, this one is probably about 30 centimeters to 30 centimeters. It's about this big. And that typically replaces about, like 3 foot by 3 foot optical space. Now, the other thing we also did was, we wanted the room temperature sometimes swings. And, twice a year, when the air conditioning comes on in the summer and when the heating comes on in the winter, all of our optical system alignment goes away. We typically spend 2 or 3 days realigning everything. So we didn't want to do that. So what we did was we then did a temperature control of this base using a water cooling chiller. And then we closed this box. We have not had to touch this thing for about 2 years. Everything is super stable, all the optical fiber alignment. Once it's done, we're done. Okay. It also turns out that if you want to replicate, we actually now then have a system where we design the blocks of functions or something like this, and then assemble them with respect to each other. And if you have to disassemble the whole thing, of course, the blocks remain aligned. And if you want to put it all back on, in an afternoon, you can get back to the experiment. You don't have to spend days and days aligning these optics anymore if you can do it this way. Okay, so that's really nice. It actually allowed us to actually then take the step where I this doesn't have to sit on an optical table anymore. So we actually put them onto instrument racks. So a lot of our CW lasers are off the table now. Okay, so the notion that all these things have to sit on an floating optical table, not true anymore. Okay. Now, the other thing is this vacuum chamber. This vacuum chamber is usually, using conflat flanges. You have to use copper gaskets, and you have to use these bolts to compress on the gaskets and so on. And in order to get the really high levels of vacuum, you have to be very careful about the material that goes in. You have to bake it for weeks at a time. And it takes typically a couple months to get the vacuum chamber ready. Okay. And in some areas, in some experiments, people make one vacuum chamber, it works well. They keep it on the vacuum for 20 years, okay? But, with the evolving quantum computer, you don't want to do that. So what we did was, okay, can we actually think about it differently? Here, we use conventional technology, and we have to bring in all the feed-throughs, all the optical windows and so on to the inside. But let's take the opposite approach, where I'll take everything else out of the vacuum chamber other than what's absolutely needed. So at the end of the day, what is absolutely needed? You need your trap to be in the chamber, right? And you need your atomic source, okay? That's about it. You need feed-throughs. So what we did was we would take a standard ceramic package, which actually already has a feed-through. We put the trap in, and then we made this little tiny lid where all of the windows are actually bolted on. We have a little bit of a ablation target, meaning we put a little bit of metallic ytterbium so we can use a laser beam to ablate it. And then we have some getter material in here. And then we weld all the side windows onto it. Okay, so now that is our UHV volume, which is about a cubic centimeter. So from like 5 or 6 liters of volume, now I went down to a cubic centimeter. Now, of course, this is hard to pump, very hard to pump. So here the idea is let's go cryogenics. Okay, so what we did. But in order to actually do something like this, to actually seal this in UHV, we now need a facility. So what we did was we created this gigantic vacuum chamber. It's big enough for you to fit one of you inside. But the nice thing about this is a one-time facility. This is like a packaging facility. What I do is then I feed my trap, package trap, and a lid. And in this thing, I actually seal this in UHV, and I pull it out, and I can ship it. So I can actually assemble like a dozen of these every day if you want to. So instead of thinking of this vacuum chamber as an assembly itself, we turn this into more of a packaging problem. Okay. Now, it was very fortunate that we were able to get funding from from IARPA to build this. It cost us about $1 million to build that facility. And then this is actually how we do the ablation loading. So usually when in the room temperature chamber, when we want to load an atom, we actually heat the atomic source to like 500 or 600 degrees. and the metallic atom sublimates. They start to come out as vapor. And then we actually shine laser beams to photoionize. And as soon as the electron leaves, then it traps. But if you have a little tiny package with a trap in the middle and the ion on the ion source just a few millimeters away, and if you want to keep this at like 10 Kelvin, there is no way you can heat part of it up to 600 degrees C. So we have to come up with a different way, and we use what's called a laser ablation. Okay, so here we actually have all of the atomic physics related lasers coming in one axis. We actually have the photoionization laser coming in the other way. And then what we do is we take a short ablation pulse laser that has just a fraction of a millijoules of energy. And then this ablation pulse laser will come in and hit the surface, and poof, we actually ablate a little bit of materials out. And then that atomic vapor flies through here, and then all these lasers actually photoionize, trap, and cool, and then we're ready to go. Okay. So here we actually looked at the velocity distribution of all the atoms coming out, and we have say, okay, you know, this is the fraction of atoms that have low enough kinetic energy to be trapped in our trap well depth, which is a good fraction of it. And at the end of the day, we say, okay, if I send one pulse in, how many atoms do I trap? Okay, what's the probability of me trapping an atom? So here you can see that with about 50% probability, I trap one atom with one laser pulse in. With about 20+%, I trap two. With about 10%, I trap three. And with about another 15%, I trap none. So about 85% of the time, I trap at least one atom with one pulse. And then, you know, we also, on the average, we trap 1.3 ions per attempt. What this means, I press the button, an atom shows up. I can press this button 20 times a second, and then I can trap 20 atoms, about 20 or 30 atoms every second. So extremely efficient, only a fraction of a millijoule, and that allows us to really go into the cryogenics. So this is actually our current setup. We started with a cryogenic a cryostat from Montana Instruments. We picked this because it has very, very low vibrations. Okay, because you know we have to come in with laser beams, and the beam has to be really stable. If there's any mechanical vibrations, we can't deal with it. So this is a closed cycle cryostat, but the sample area is extremely stable vibrationally. But the downside is this cryostat, the way they make it, they don't support UHV. But that's okay, because we have a secondary package of cryogenics that actually encloses the atom over here that actually can give you an extreme vacuum. So this is what the setup looks like. Over here on this is a cold finger, this gold thing back here, and we have a trap. This is a lens that actually images the atoms. You can actually trap some atoms here, and they remain extremely stable. Meaning once you trap them, unless your laser goes out of lock, the chain stays there for days, okay, because the vacuum is so good. There's no collision virtually. And then, as I mentioned earlier, we build these blocks, optical blocks, and then we assemble them around it so that we can bring all of these lasers through fiber. So it's a very modular assembly, and then we can actually get to very low levels of heating. So this is what our lab actually looks like. We now have a cryostat. We have these optical boxes that actually delivers different functions to the traps. There's an ablation laser here. This is actually our CW laser systems. This one is actually a stabilization. We have a little cavity that we use to lock the frequency of the lasers. This is a Raman laser. This is the modulation that's needed for the Raman. And then we actually close all the boxes. And this is our experiment now. Okay. All right. Then we asked the question, okay, we did this at cryogenics. Can we actually do this, just run this thing at room temperature? So here, what CoQuanta, our collaborators, have done is they developed this little technology to build this little tiny ion pumps. Okay, so this ion pump is about an inch, maybe 2.5 centimeters in diameter, and about 5 centimeters tall. And they actually attach that to this little vacuum chamber. So in this little room temperature vacuum chamber, we have a getter pump inside, and then we have a little ion pump. And this gets assembled in this 10 to the minus 10 torr UHV facility, and then they pull it out and they ship it to us. Okay, so I was a little skeptical whether the vacuum will be good enough, but we decided to give it a shot at trapping anyways. So now this is our vacuum chamber, and the vacuum chamber literally fits on the palm of your hand, okay, at room temperature. And now we put a camera, we put our imaging system, we put our camera, all the lasers beams that needed. So now instead of having a big vacuum chamber with all the assemblies, now we have a tiny little chamber with this big optical assemblies. And we were able to trap some ions and keep them here. So now the next question is, can you actually integrate this more? Okay. So here is our next attempt, where we try to fit everything that's needed to trap an ion into a 30 centimeter by 30 centimeter box. That was our attempt. So the little package is actually mounted upside down onto this aluminum plate. You can see the little bit of the ion pump here. All of the electrical wiring is done through this little box with the cables. That's our RF resonator. And now we actually also use these reflected optics with a photonic crystal fiber with very different wavelengths, like 370 nanometers and 935 nanometers can actually propagate as a single mode in this photonic crystal fiber. And then we use reflected optics so that there is no chromatic aberration. So we're using all of these little techniques. Now was able to fit all of the trapping and cooling and ablation onto this little tiny plate. Okay, so that is kind of the most compact optical system we have. The lower floor is entirely there to do the imaging, so we can actually do state detection and imaging of the ions. And the whole thing now sits on a box that's about this big. Okay, so, and this is not the end, right? I think it's really a lot of these things is trying to reduce the size of everything else that controls this little tiny quantum computer. So all of you have a lot of room to be imaginative and come up with new technologies so that eventually our quantum computers can actually be the size of a desktop and a laptop. I think all of the technology capabilities are there. So if you look at just the brief history in the last 10 years or so, in 2016, ion trap experiments looked like this. In 2018, we built a system that was in a box. This is kind of my lab where all of these optical functions are now modularized. And this is kind of where the system really became something that you can actually literally lift with your hand. It's a little heavy, but you can lift it. Now, what's really interesting in this kind of time frame is people started to actually now use the integrated photonics to bring all of these laser beams, which are currently now coming from the outside and focus back onto the thing. And they're actually fabricating that through integrated photonic technology, integrated optics. Okay, so now you can think about a world, and here, they have these grating couplers where you propagate the beams on a waveguide underneath the surface, and then they have grating couplers that takes the beam out into free space and now can focus onto the atoms, and they were able to demonstrate a whole host of functions this way. So you can now think about a world where a lot of these optics, which is currently coming from the outside, can eventually be integrated onto the chip itself. So if you can get to very good vacuum at room temperature, and if you can actually start to pull these integrated photonics into the mix, an ion trap quantum computer can be eventually packaged into a very, very small volume, right? We don't need dilution refrigerators, which is not going to scale. Okay, so I think this is kind of the technological vision. And if you think about 5 years from now, ion trap quantum computers will be built this way. There are lots of interesting research and technology development you can actually start today to try to get ahead of the curve. All right, so I think that's kind of the technology side of things. Any questions? So I'll tell you a little bit about where we are with how big of a quantum circuit we can run. Okay, that's the next topic. Yes.
How long can you operate ion?
That little tiny ion pump has been operating for about 2.5, 3 years now, and they still seem to be working fine. Again, it's a matter of what is actually outgassing. Now, we had a very clever choice of materials. So that whole chamber is built out of titanium. So if you make things out of stainless steel, then hydrogen keeps coming out. But if you build it out of titanium, titanium actually is there's a sublimation pump. It actually is a getter. So if you pick the right material, then what's limiting is your windows. They actually permeate hydrogen and helium. So that becomes your limitation. You have to, so you have to pick the right material. The permeation is low and so on. So there's a lot of kind of materials choices and engineering you can do to make sure that the amount of gas coming in remains small compared to the amount of gas you can pump out. And hopefully we can get to much lower vacuums. Now in that little chamber, we're seeing about a vacuum of 2 times 10 to the minus 11 with that little tiny ion pump. which is actually remarkable. Okay. All right, so now I'm going to talk about what can you do with some of these quantum computers. And this is actually a list of systems that we have at Duke University, where we designed these systems to have certain capacities, and some of these things are built and now have been characterized, other things that are currently under construction. And what was really interesting about this exercise is now with these systems, I showed you some early examples of that 5-qubit system running different experiments. These are the systems. We saw this one was the bit one that I showed you that was built under IARPA, and we have these many other systems that we have constructed over time. And these are actually the list of collaborations we have done. So these are people who have ideas about what kind of experiments they want to do, what kind of quantum circuit they want to run. They say, okay, you guys have a small but generally programmable quantum computer. Can I actually look at this and look at Bayesian gains, generative modeling, machine learning models, QAOA, benchmarks, and all these things. And you can see that the list is really long, right? So there's a long list of people who come to us. These mostly theorists. I have an idea of this quantum circuit or quantum model. Can I run this on a quantum computer that you guys have? So we actually generally do that. And yeah, the list goes on. So the real interesting idea is right now, if you look at how many qubits you have in your system versus what is the operational error in your system, we're kind of down on this corner. Yeah, we're kind of down on this corner. Maybe somewhere between 10 to 100 qubits. Maybe the error rates are, if you have exactly 2 qubits, you may have better than 99.9% errors, but typically you're kind of up here. And this is actually remarkable, but not very interesting or exciting quite yet, because any system that have less than maybe 45 qubits, 40 some qubits, you can actually classically simulate by brute force, no matter how many gates you can concatenate. But if your error rate is very low, then you can start to run very deep circuits. But in order to run, circuits with 100,000 gates, you really need your errors to be in that regime, which we're not. What we're really trying to do is, can we improve the hardware so that we can build a bigger system, meaning more qubits, but also reduce the errors so we can run deeper and deeper and larger circuits, because that's where you cross this line, where things cannot be simulated anymore. Okay. The second question is, are there some interesting problems over here? That requires, say, 100 qubits and 10,000 gates. I don't know what they are, but if there's some really interesting problem that are over here, this problem cannot be simulated with classical computers because system is too big. Okay, so if your technology can meet a problem, then I think there is some really interesting opportunity for you doing something really useful. There are some software work we can do, optimizing algorithms to take this problem and try to do it with either smaller number of qubits or smaller number of gates. Right? That's all software optimization. You should be able to do some of that. And then you can also do some what's called an error mitigation. Right? How can you actually identify what your error is and try to control them or improve them better, so you can effectively run much deeper circuits. And the minute that you can actually improve the hardware and software and make them meet, then I think you should be able to start doing something very interesting up here. And we're not very far. I don't think we're very far from being able to get to that point. Okay. All right. So let me. So I'm going to go a little bit over 2 hours, if you don't mind. So I spoke earlier about how do you think about scalability in terms of what useful things you can do with your computer. And usually there can be device level metrics, like say number of physical qubits in your system, what's the gate fidelity, what's the clock speed, and these are important metrics. But when you buy your cell phone today, or when you buy your smartphone, you usually don't ask the question, how many transistors do I have on this phone? You don't ask that question anymore, right? That's because that's not important. What's important is, how many photos I can store, how quickly can I get to the internet. It's really more of a functional thing, right? When you buy a car, you don't ask the question, how many bolts do I have in this car? You think about what is the gas mileage? How many people can I actually, how safe it is? There's usually a functionality. So these device level metrics are sometimes useful and informative. Oops. But they don't usually tell you, they don't translate to what a user can do with this computer. Okay, and this has been a problem with classical computers for a while, and the classical computers engineers actually have a solution. They do what's called an algorithm-based benchmarks. So the classic example is this thing called spec benchmarks, and you can look up spec benchmarks. This was actually established by a consortium of industry players in 1988, and that's when they start building. Different vendors started building different computers, and the customers are saying, I want your performance to be benchmarked. Okay, and then they're saying, and all the vendors had their own way of doing it. And the users are saying, okay, I can use your metric to compare your current version to your previous version and see how much improved it is, but I can't trust with your metric to compare with somebody else's computer. Right? So the industry had to come together and come up with benchmarks. And this goes like this. There are many things people want to do with a computer. Let's say I'm interested in playing games with a computer, and therefore graphics is important. I'm interested in crunching some numbers for my experiments, and therefore, number crunching is important. I do a lot of integer addition. So there are many different use cases, and what they do is they come up with a long list of typical use cases that people use a computer for. And then they create an algorithm that tests capabilities and performance against that use case. Okay, so this spec benchmarks, if you go in, they have a list of like 20 or 30 different algorithms, and they're all very well specified, and you're supposed to run that and then publish the results. Okay, so when you build your computer, and when you want to buy a computer, you can actually say, okay, this line of testing represents what I'm interested in. So I'm going to compare a whole bunch of vendors against this metric, and then I'm going to pick my choice. If you're a vendor, you can say, I'm interested in this segment of the market. I'm interested in building computers that can do better video games. Then these are the important metrics. I'm going to put together a system where I do really well on this. Right? So it's really a communication between the users and the makers, or makers and takers, to communicate, to say what's important to them. So this is what's called a algorithm-based benchmarks. So in this Quantum Economic Development Consortium, this is an industry consortium in the US. About 2 or 3 years ago, they came together and say, okay, let's think about how to measure quantum computer performance based on useful algorithms. So they started with a few known algorithms, and to say, I'm going to figure out how to benchmark the performance of a quantum computer based on each of these algorithms. So this is what they did. Okay, so on the x-axis, you have the circuit width. This is how many qubits you have to run that algorithm. And this is circuit depth. This roughly says how many gates do I have to run. Okay, so in a quantum Fourier transform, a 2-qubit quantum Fourier transform requires 2 physical qubits and maybe about 16 gate operations. A 3-qubit quantum Fourier transform requires 3 qubits and maybe, I don't know, 30 odd gates and so on. And it turns out that it actually now traces a trajectory to go from 2, 3, 4, 5, 6, 7 qubit Fourier transform. Okay, so, and then what they do is, okay, if I run these algorithms, what's my success probability to get to the right answer? And that's plotted in the color plot. Okay, so generally, as you go up on this corner, you need more qubits, you need more gates, and therefore the fidelity goes down. But when you're down here, your success probability is reasonably good. So that's a very reasonable thing to do. And then what they did is, okay, now, and from here, and they actually chose about half a dozen, maybe 7 or 8 different algorithms and used it as a benchmark, and they ran these kinds of standard circuits on all of the quantum computers that they had access to. So from here, what we did was we defined what's called an algorithmic qubit. So algorithmic qubit is not how many qubits you have in your system, but it represents how big of a circuit you can run. Okay, so here, if you have n algorithmic qubits, it means I can use n qubits, and then I can operate circuits that contains up to n squared entangling gate operations. Meaning if my algorithmic qubit is 10, I can use 10 qubits and run circuits that contain about 100 entangling gate operations. If my algorithmic qubit is 20, then I have 20 physical qubits that I can use to run an algorithm that has up to 400 entangling gate operations and so on. So this actually measures both the number of qubits you can use in your system and how many gates you can run. Okay, and I'm going to actually measure this against very specific algorithms that were actually outlined in this work. Okay, because I can't run this for arbitrary number of gates. but I'm going to do it on a list of finite number of applications that represent different use cases, very similar to how spec benchmarks does it. Okay. It turns out that this is called a volumetric benchmark, not just about physical number of qubits, but also gate depth as well. And it actually tells you how big of a quantum circuit you can run. And if you have an AQ of 60, yeah. If you have an AQ about 60, that means I can run on 60 qubits, I can run about 3,000 or 4,000 entangling gate operations. And that system is not going to be simulatable in most cases. Okay, so we're trying to really go after this AQ. And as AQ goes up, at some point you're going to get into a regime where you can't simulate this stuff. Okay, so this is that now back at IonQ. Our current system, ARIA, which is on the cloud, actually has an AQ of 25. What this means is these are the 6 algorithms that were specified that were non-trivial. Hamiltonian simulation, phase estimation, quantum Fourier transform, some form of VQE, amplitude estimation of Monte Carlo. And these algorithms, the gate depth actually scales exponentially with time. And these 3, the gate depth scales as n squared. So you can see that as you approach, for these algorithms, they actually approach this corner, and this gray box that says it's 25 qubits and 25 square, which is 625 entangling gates. And that draws this box. And all I'm saying is for these 6 algorithms, everything in this gray box has to pass, right? And that defines what the AQ of the system is. Now, we're allowed to do a couple of things. One is you're allowed to use a compiler, meaning if you have a unitary operator, and if your system allows more efficient way to implement that unitary, because you're auto-connected and so on, you're allowed to take that unitary and break it down into whatever gate sequence you want, as long as the unitary is the same. Okay, that seems like a fair thing. And the other thing is we actually allow what's called the error mitigation. If you actually have a mitigation, if you have a very systematic error, and if you can somehow kind of mitigate those errors, you're allowed to do that as long as you're not cheating. Cheating here means if you know the answer and try to filter the answer, that's not fair. But if you have a systematic way of reducing the contribution of error to get to the right answer, then you should be allowed to do that. Okay. Oh, I don't have one, but we actually have a new system called Forte, and there the algorithmic AQ number is 29. Okay, we actually can do much deeper circuits that way. Yes. Circuit width is the number of qubits. So when you say 25 phase estimation, this is a 25 qubit phase estimation algorithm. Circuit depth is how many entangling gate operations you need to do to actually draw that circuit out. Okay. All right. So this brings to the very last element, which is what can you do? What can you do interesting things with this system? And here, I'm going to go to this classic example of a machine learning problem. Okay, so machine learning problem, and this is called an image classification. And here what I have is a bunch of cat pictures, a bunch of dog pictures. Okay, so when a baby is born, the brain is very clean. They don't know what a dog or a cat is, right? But as they grow, they see a lot of dogs, they see a lot of cats. And the parents tell you that's a dog, that's a cat. And then they start to form some model in their brain, right, that can actually start to identify cats from dogs. And the goal is to see if we can build a statistical model in a classical, in a computer, so that it can actually classify those things. So what typically happens is you take your input, which is your cat picture, and then classical convolutional neural networks actually go through many iterations of convolution to compress that data, so that this has a lot of pixels. But at the end of the day, what you're looking for from that dog or cat is a feature, right? Cats tend to have a more circular face. The eyes are a little bit more sharp, right? And then the snout is maybe a little bit shorter, and you have these whiskers, and the ears tend to be pointy, right? So there are characteristics of dogs and cats that are very, very different. Can we actually compress and only capture the important characteristics in a much smaller dimension data? That's the first thing you do. And then you actually create a statistical model with lots of parameters that you can tweak. So that if it's a dog picture, then you steer your parameters in one direction. And so you steer the parameters in some way that all the dog pictures tend to fall on this side and all the cat pictures tend to fall on that side. Once you have a model that's built, then you give it a new picture that's never seen before and see if you can actually distinguish dog and a cat. And then you see the accuracy of how we can do that. Okay, so that's kind of typically how a machine learning works. So now the next question is, can you do this with quantum? Okay, so we had some collaboration with a research lab at Hyundai Motor Company. And they gave us a toy problem about 1.5 years ago. And this toy problem looks like this. It's still a toy problem because it's not a real problem they wanted to look at. But they gave us a picture of road signs from Germany. And there are 43 different one of them. And they say, can you build a quantum machine model that can start to distinguish these road signs from each other? Okay, I'm going to encode the data into a quantum state, and I'm going to create a quantum model to see if we can do the classification problem. Okay, all right, so that's a challenge. So the first step is, these images are still very big. These are not very big, but they're like 30 by 30 pixels, and that's still like 1,000-dimensional image. So we don't want to put it. We don't have 1,000 qubits to put them on. So we actually had to compress it. So what we did was we did classical compression, and this is kind of what's called an autoencoder using a neural network, and that starts from the input data, which is a full image, and then it compresses it down to a much shorter vector that captures the essential features that are important. Okay, and that's a vector in what we call a vector in the latent space. Now, in order to make sure that our encoding process did not throw away a lot of important data, what we did was we actually did a decoding and reconstructed the image. Okay, so if the original and the reconstructed image look the same, that means when I compressed it, I kept all the essential elements, and so that I can reconstruct it back. So they look pretty good, but here you see that in this triangle, right, there's a little confusion with a triangle and a circle, right? So that autoencoder was not perfect. So we actually decided to come up with a slightly improved version of it, where we actually shifted some, just only look at local connected networks. And then now with this, we got a much better data. You can see that this one and this one actually now looks the same. So we had a much better encoded data. And in the middle, we have a highly compressed, very short latent vector that captures the essential elements of this image. Okay, so what we do is then, I'm going to load that latent vector. I'm going to load it in the quantum state. Okay, and then I'm going to create a quantum model that I'm going to train to see if this quantum model can actually start identifying road signs. Okay, so the quantum model looks like this. It's got up to 16 qubits at the input. And then I apply 4 different unitaries. And these unitaries are 2 qubit gates, 2 qubit operators, the U1, U2, U3, and U4. Okay, and the U1, 2, 3, 4 is constructed like this. It's got 3 CNOTs and maybe 7 single qubit rotations. And these single qubit rotations have 3, 6, 7, 8, 9, 12, and 15 parameters. Okay, turns out that if you have an arbitrary 2 qubit unitary, you can describe it with 15 independent parameters. And that's the very generic circuit to do that. The most generic 2 qubit unitary operators you can make. Okay, 15 independent parameters. So each U has 15 parameters. But I only chose to use 4 of them. Okay, so U1 is an operator we apply to nearest neighbors. Okay, so when you have 16 qubits, there are 15 nearest neighbors you can do, and we apply U1 to each and every pair, nearest neighbor pair. So 1 and 2, 3 and 4, 5 and 6, and so on, and then 2 and 3, 4 and 5, and so on and so forth. Okay, so there are 15 unitary operators you do, and then on the next layer, we apply it to next nearest neighbor, every third one, every second one. And then the next one, you apply it to every fourth. And the next one, we apply to every eighth. Okay, so there are 15 of these things, 7 of these, 3 of these, and 1 of those. Okay, now, then I can scale the model. If I only use 4 qubits, then I have a model that looks like this. 3 U1s and 1 U2. It's a 4 qubit model. I can go to an 8 qubit model where I have 7 U1s, 3 U2s, and 1 U3. I can also go to a 16 qubit model where I have 15 U1s, 7 U2s, 3 U3s, and 1 U4. Okay, so I can create those 3 different models of different complexity and see how it works. And then what we do is now with the training, with the data, I can actually start to tweak these parameters so that when I actually do some measurements at the end in multiple bases, different road signs will come out in very different outputs. That's more distinguishable. So I'm going to tweak these parameters in the model and train it so that these can actually start to discriminate the images after this unitary transformation. Okay, so that's how a quantum machine learning model works. Actually, I'm just going to go to the final slide, which is the result. Okay, so this is for 4-qubit model. That's for 8-qubit model, and that's for 16-qubit model. Okay, the 4-qubit model only had 30 parameters, and it's a very simple model. So when you're trying to discriminate two different categories of images, it actually does pretty well. It actually can tell that with like 90% accuracy. But when you go to 4 categories, 6 categories, 8 categories, and 10 categories, then the structure of your model is way too simple to capture this very complex data structure. So your accuracy drops very quickly. Okay, so the orange is kind of an ideal quantum simulation, classical simulation of that quantum model. And for 4 qubits, you can very easily do that. But you can see that as you increase the number of qubits in your model and add more parameters, your accuracy goes up. And that's because your quantum model can actually capture more structures and discriminate more different patterns more effectively. So here you're doing pretty well, right? Even with 10 categories, you can succeed with about 60% probability. And then these gray lines, bars, are actually trained on a real quantum computer using IonQ Aria. Okay, so yeah, there's a gap between an ideal simulation and a real quantum computation, but it's actually not too bad. Meaning, that's because of your finite errors, but you can actually run these things and do a reasonably good job of classifying images. The question is, why is this interesting, right? Yeah, the classical computers can do that too. Why is this interesting? I think one of the things that we're finding out is, remember, in this quantum convolutional circuit, as you go from a 4-qubit model to 8-qubit model to 16-qubit model, we have parameters that we have to train are 30, 45, and 60. Okay, and with 60-parameter quantum convolutional circuit, you're doing a pretty good job of discriminating images. It turns out that in order to use a classical convolutional neural networks to get to a comparable performance, you need models where you have to use about 59,000 parameters, meaning you need a lot more parameters that you have to train to get to the similar performance. I think at least what this means is, with quantum models, you can use much fewer parameters to construct a very, very complicated model in Hilbert space that can actually capture structure of an image data. I think that's what this is saying. Okay, and if this ratio continues to improve as you get to larger and larger systems, then maybe there will come a time where quantum models can be much more accurate with much fewer parameters. That means it can be trained much more easily with much fewer data. And that, I think, is an opportunity where we can potentially get some useful gain. So this is an example where, yeah, we can actually do some real world problems with a quantum computer today. Okay, these quantum computers are not these things that can only do like real quantum mechanical problems or simulations. We can actually come up with realistic algorithms and find opportunities where quantum models can actually give you an edge compared to classical approaches. Okay, with that, I would like to thank a lot of my collaborators over the years. This is actually a picture from a Duke Quantum Center that opened up in, we officially launched it about a year ago. And we actually have, probably over 100 researchers that are in the same building, trying to build this vertically stacked quantum computer that people can use to develop applications and use cases and things like that. And I'd also like to thank my colleagues at IonQ. All right, with that, I'd like to thank you for your attention and happy to take any questions. Yes.
계산을 쓰기만 하는 게 아니라 레지스터나 플래시 같은 메모리가 직접 관여를 하고 있는데요.
예.
퀀텀 컴퓨팅을 할 때도 주로 로직만 설명을 해주셨는데 퀀텀 메모리 같은 게 필요한 거예요? 아니면 그냥 클래시컬 메모리로 메모리를 필요한 거예요?
예. 그 질문은 이제 클래시컬 컴퓨터에서는 데이터를 이제 메모리에 스토어했다가 이게 레지스터 모델이니까 그거를 그 레지스터 갖고 와서 프로세싱을 한 다음에 다시 치우고 다음 거 가져와서 하고 이런 모델인데 지금 보면 지금 더미넌트한 양자 컴퓨팅 모델은 그렇지가 않고 그냥 메모리에다가 집어넣은 다음에 거기다 바로 컴퓨테이션 하는 그런 모델입니다. 그래서 이게 이 메모리 시프팅을 많이 하는 거는 아니고 저희가 지금 생각하는 스케일러블한 시스템들은 이제 메모리 사이즈, 그러니까 데이터를 넣어놓는 메모리 사이즈가 커질수록 컨트롤러도 같이 스케일을 해서 레지스터가 점점 커지는 그런 모델을 생각을 많이 하고 있습니다. 그래서 그 퀀텀 근데 그게 말이 되는 게 양자 컴퓨터에서는 이제 그 게이트를 로컬하게 해도 인탱글먼트가 많이 있을 경우에는 스테이트가 굉장히 많은 스테이트가 동시에 바뀔 수가 있거든요. 그래서 지금은 그런 모델을 생각하고 있고 그렇기 때문에 지금 그 양자 알고리즘의 가장 큰 버틀렉은 우리가 이 양자 데이터를 어떻게 양자 스테이트에다가 효율적으로 업로드를 할 수 있을 것인가. 그리고 그걸 업로드하는데 서킷이 필요하거든요. 그래서 이제 저희가 지금 보여드린 모델은 이 클래시컬 컴프레션을 많이 해가지고 클래시컬 데이터를 굉장히 짧게 만든 다음에 효율적으로 양자 컴퓨터에 올려주는 방법이 하나가 있고 다른 방법은 이제 양자 힐버트 스페이스가 엑스포넨셜하다는 걸 사용을 해서 굉장히 덴스한 데이터를 바로 로딩하는 방법들도 사람들이 고민을 많이 하고 있습니다. 그렇게 해서 일단 데이터가 로딩이 되면 그 다음엔 프로세싱을 해야 되고 굉장히 많은 데이터를 집어넣는 거는 양자 컴퓨터에서는 아직까지는 힘듭니다. 왜냐하면 그 인풋 아웃풋 밴드위드가 작은데 진짜 장점은 인풋이 작고 아웃풋이 작더라도 그 중간에 컴퓨테이셔널 스페이스를 무지하게 크게 활용을 해서 필요한 프로세싱을 얼마나 효율적으로 할 수 있냐. 이제 그게 퀀텀 컴퓨터의 가장 쓸모있는 모델이기 때문에 그런 식으로 생각하셔야 될 것 같아요. 인풋은 컨스트레인트가 있고 컴퓨테이셔널 스페이스는 굉장히 크고 아웃풋도 컨스트레인트가 있고 그런 경우에 컴퓨테이션이 이제 양자 컴퓨터에서 현재로서는 잘 어울리는 시스템이고 그거 다른 모델로 가려면 좀 다른 하드웨어 모델들이 필요할 것 같습니다. 예.
는 아무 문제나 얼마나 큰 사이즈의 문제도 일단 풀기는 쓰지 않고 오래 걸릴 수 있겠지만
예.
메모리 그런 것만
예.
직접적으로 관련이 되는 게 이 에러웨이트가 마이너스 91수
예.
가야 된다는 조건이 있는데
예.
마이너스 30% 얼마나 시리어스한 문제니까 괜찮은.
그러니까 그거 좋은 질문인데요. 사실 아까 그래서 제가 알고리즘의 큐빗이라는 컨셉트를 얘기를 해주는 게 클래시컬하게는 그 게이트 에러가 무지하게 낮기 때문에 사람들이 사실 이 컴퓨테이션을 페일한다는 거를 많이 어스움을 안 해요. 근데 물론 거기도 페일러가 있죠. 뭐 코스믹 레이가 와서 페일을 한다거나 어쩌다가 뭐 오류가 날 수도 있거나. 근데 오류의 그 가능성이 워낙 작기 때문에 굉장히 효율적으로 그걸 미티게이트하는 방법들이 있습니다. 클래시컬하게는. 근데 양자 컴퓨터는 뭐 fault tolerant한 머신이 나올 때까지는 그 시간이 얼마나 걸릴지 모르지만 그때까지는 오류랑 같이 살아야 돼요. 그러기 위해서는 그 시스템을 계속 임프루브해서 게이트 에러를 점점 줄여주거나 그래서 우리가 시뮬레이트를 할 수 없을 만큼 큰 시스템을 만들어 깊은 서킷을 할 수 있을 때까지 임프루브하거나 아니면 그 알고리즘이나 하드웨어나 데이터의 스트럭처를 잘 이용을 해서 에러 미티게이션을 해줘야 됩니다. 그런 에러들이 그 결론을 많이 바꾸지 않도록 미티게이션 많이 해줘야 되고 이제 그런 트랙들이 굉장히 중요할 것 같고 어떤 컨비네이션으로 우리가 의미 있는 문제를 쓸모 있는 문제를 풀 수 있는 그 범위에 도달할지 거기에서는 아직까지는 이제 오픈 퀘션도 많고 기회도 많이 있다고 생각합니다. 역으로. 그래서 이제 그 예를 들어서 우리가 한 60개 정도의 큐빗을 가지고 3,000, 4,000개 정도의 게이트를 릴라이블하게 할 수 있는 그런 시스템을 만들었다고 했을 때 그거 갖고 뭘 할 수 있느냐. 모든 문제를 다 풀 수는 없지만 어떤 문제가는 풀 수가 있을 것 같은데 이제 그걸 찾는 게 머신러닝이나 이런 데서 좀 힌트를 우리가 많이 보고 있다고 말씀드릴 수가 있겠습니다. 예. 예.
에러 마이티게이션이라는 지금 말씀하신 에러 마이티게이션
예, 하는 거 얘기하는 겁니다. 예, 그 에러 미티게이션이라는 거는 그 시스템의 에러가 그 결론을 이제 바꾸는데 물론 에러가 워낙 도미네이트를 하면은 노이즈밖에 안 나오겠죠. 근데 이제 그 에러가 그렇게 도미네이트하기 전이라면은 우리가 그 에러의 특성을 잘 찾아서 그런 에러의 효과들을 서프레스 해줄 수가 있습니다. 예를 들면 어떤 게 있냐면 우리가 예를 들어서 케미스트리 시뮬레이션 한다. 그러기 위해서는 이제 오비털들의 일렉트론이 들어가 있다는 걸 전제를 해가지고 이제 막 계산을 돌리는데 그 케미스트리 프로블럼에는 시메트리가 있습니다. 시메트리가 뭐냐면 전자의 개수가 줄어들지 않아요. 전자가 트랜지션하는 건 뭐대로 하지만 전자의 개수가 더해지거나 없어지거나 하진 않거든요. 근데 그런 시메트리가 있으면 우리가 결론, 예를 들어서 우리가 양자 컴퓨팅을 쭉 해가지고 결론이 나왔는데 우리가 측정을 해 보니까 전자의 개수가 바뀌어 있더라. 그렇다는 얘기는 어딘가 결정적인 그 오류가 났다는 얘기잖아요. 그럼 그런 데이터들을 그냥 버릴 수가 있어요. 이거는 오류가 난 게 확실하니까. 그러니까 에러 디텍션을 하는 거죠. 시메트리를 통해서. 그렇게 해가지고 우리가 뭐 10,000개를 돌려가지고 그중에 3,000개는 에러가 난 게 확실하기 때문에 버리고 나머지 7,000개만 가지고 분석을 한다. 그러면 그 전반적으로 에러가 있는 것들을 우리가 필터를 굉장히 제대로 해줘서 그 나머지 결과들이 훨씬 더 좋은 결과처럼 나올 수가 있거든요. 이제 그런 것들이 에러 미티게이션의 핵심입니다. 시스템에 시메트리가 있으면 그 시메트리를 활용을 해서 에러가 생겼다면 어떤 식의 에러가 생겼는지, 또 우리가 그런 에러를 시스테매틱하게 서프레스 해줄 수 있는지, 그런 여러 가지 테크닉들이 있습니다. 그래서 저희는 이제 그 디바이어싱이라는 테크닉을 굉장히 많이 활용하는데 저희 시스템에는 굉장히 잘 적용이 되는 거고, 뭐 IBM이나 다른 회사들도 이제 나름대로 그런 에러 미티게이션 테크닉들을 통계적으로 그리고 수학적으로 릴라이블한 그런 테크닉들을 많이 개발을 하고 있습니다. 예.
알고리즘 큐빅 때
예.
개수가 얼마나 걸리는 거예요?
예, 근데 그게 이제 좋은 질문인데, 저희는 이제 회사에서는 그 로드맵을 만들어서 푸시하고 있습니다. 그러니까 저희가 그 원래 재작년에 22개, 작년에 25개, 올해 29개, 내년에 35개, 그 다음에 이제 64개로 가야 되는데, 이제 그거를 이제 사람들이 이렇게 나름대로 그거를 어떻게 할지에 대해서 로드맵이 있으면 그 로드맵을 만들 때는 이걸 어떻게 하는지 정확히 알지 모르지만 계속 이거 어떻게 할지 고민합니다. 마찬가지로 그 무어스 로에도 이 로드맵이 있으면 뭐 3년 뒤에 이게 4배가 돼야 된다 그러면 대부분의 경우는 I don't know how to do it. 네? 근데 이제 그게 그 로드맵에 가야 되기 때문에 뭐 온갖 종류의 이게 고안을 하고 투자를 하고 그래가지고 방법을 찾아내거든요. 결국 그렇게 하는 거니까. 그래서 제 생각에는 이제 그 클래시컬 시뮬레이션이 어려워지려면 알고리드믹 큐빗이 한 40개 넘어가면은 클래시컬 시뮬레이션이 굉장히 비싸집니다. 그래서 이제 50개, 60개 가면은 굉장히 못할 것 같고, 그래서 지금 저희가 이제 29개까지 왔기 때문에 내년에 만약에 35개 갈 수 있으면 그 다음에는 이제 그 시뮬레이션이 어려워지는 단계로 진입할 수 있지 않을까. 제가 보기엔 앞으로 몇 년 안에 할 수 있을 것 같습니다. 저희 기술을 따라가면. 예.
그런 바스켓을 필요한 사람들이 제일 지금 고민하는 테크놀로지가 뭐예요?
지금은 에러 컨트롤입니다. 저희 시스템에서는. 뭐 큐빅 잡는 거 이런 건 전혀 문제가 없는데 아직까지 저희 시스템에서는 시스테매틱한 에러가 많습니다. 시스테매틱하다는 게 그 레이저 파워가 플럭처를 해가지고 게이트를 돌리는데 약간 오버 로테이션, 언더 로테이션 온다거나, 아니면 저희가 2큐빅 게이트를 쓰려면 모셔널 디그리 오브 프리덤을 써야 되는데 그 모셔널 프리퀀시가 뭐 약간씩 드리프트를 한다거나, 뭐 그런 굉장히 서틀한, 특히 이제 에러가 막 10의 3승쯤 가면은 굉장히 서틀한 그런 이슈들이 있는데 그런 것들을 찾아내면 고칠 수가 있어요. 그래서 아직까지는 제가 보기에 한 10의 그러니까 AQ 뭐 35에서 60까지 가는데 가장 핵심적인 거는, 다른 기술은 다 괜찮고 결국은 그 에러 컨트롤 어떻게 하느냐, 컨트롤러를 얼마나 잘 만들고 그런 에러를 얼마나 잘 이해하고 거기에 효율적인 미티게이션 테크닉을 개발하는지, 그런 것들이 지금 시스템 레벨의 챌린지가 훨씬 많습니다.
혹시 저희가 아이언트 몇개 할 수 있냐가
트랩은 뭐 저희는 지금 뭐 60개, 100개 뭐 트랩은 얼마든지 할 수 있다. 그거는 문제가 아니고, 그걸 얼마나 활용해서 풀 서킷, 이런 쓸모 있는 서킷을 쓰느냐, 그게 가장 핵심적인. 예.
N개 그 큐빗이 있으면 이게 N승의 그 피보트 스페이스에서 베이시스가 있는 거고,
예.
그 중에 하나의 어떤 스테이트를 우리가 이니셜 스테이트를 만든 다음에 게이팅을 한다는 의미는 뭐 퀀텀 오퍼레이션에서 어떤 또 다른 어떤 스테이트로 오퍼레이션 하는 거잖아요.
예.
이니셜, 파이널 스테이트. 근데
예.
그 오퍼레이션 하는 게 3,000가지의 다른 오퍼레이션이 있다라는 말씀.
예, 근데 그게 이제 원칙적으로 얼마나 많은 가능성이 있느냐 하면 arbitrary 그 서킷을 할 때는 그 exponential하게 많은 게이트 디컴포지션이 일반적으로 필요하거든요. 그러니까 그거를 이제 arbitrary하게 하기 시작하면 근데 사실 대부분의 알고리즘들은 arbitrary한 게 아니기 때문에 그 알고리즘의 스트럭처가 있지 않습니까? 예, 그래서 저희가 얘기하는 거는 3,000개가 다가 아니라 3,000개까지의 이 entangling gate 오퍼레이션을 해도 우리가 그 측정하는 레퍼런스 알고리즘에서는 답이 높은 확률로 나온다. 예, 그런 걸 말씀드리는 거죠.
그러면 이제 우리 양자역학에서는 뭐 해밀토니안이 주어지니까 그 아이겐 스테이트를 풀기 원하지 않습니까? 예를 들어서 그런 걸 하려면 사실은 그냥 퀀텀 오퍼레이션을 뭐 몇 번 한다고 되는 문제가 아니지 않습니까?
예.
그런 이니셜 스테이트는 분명히 그라운드 스테이트는 아닐 텐데 뭐 그라운드 스테이트를 찾아간다든지 그런 거는 어떻게 이루어질 수 있는 건지.
예, 그러니까 이제 그게 이제 우리가 원하는 퀀텀 알고리즘인데 아까 그 해밀토니안 시뮬레이션 같은 경우는 n 큐빗의 이 뭐 아이싱 시뮬레이션 같은 거를 이제 하는데 그러면 n 제곱의 인탱글링 게이트가 있으면 다 할 수 있어요. 근데 이제 그게 어떤 피직스를 시뮬레이트 하는지에 따라서 그 알고리즘의 뎁스가 n 제곱에 비례할 수도 있고 n 세제곱에 비례할 수도 있고 예를 들어서 쇼 알고리즘 같은 경우는 n 세제곱에 비례하는 알고리즘입니다. 예, 그래서 이 알고리즘 뎁스가 여러 개 있으니까 그 구체적인 문제를 어떻게 푸는지는 그 컴퓨테이셔널 스페이스가 사실은 훨씬 더 복잡한데 그런 걸 다 벤치마크를 할 수 없으니까 저희는 일단은 이렇게 간단한 벤치마킹 모델을 활용하는 겁니다. 예.
10x10 마티스라면 그게 n
1000개 그 10x10 2디멘션 라이트는 100개고 그걸 세제곱하면 밀리언 오퍼레이셔널 예. 그렇죠. 그렇죠. 근데 이 해밀토니안 시뮬레이션 같은 경우 저희가 하는 거는 n 제곱이기 때문에 너무나 간단한 거고. 그러니까 결국 알고리즘의 그 스트럭처에 따라서 그 깊이가 결정이 되는 겁니다. 예.
함께 보신 주제를 가지고 50개 올토는 안 되더라도
예. 아니 어렵지 않습니다. 그러니까 그게 이제 제가 아까 시간이 없어서 좀 넘어간 게 있는데 이게 이제 그 2002년도 그러니까 이게 20년도 넘은 얘기인데 데이비드 켈핀스키, 크리스 먼로, 데이브 와일런드 이게 네이처의 이 QCCD 아키텍처라고 이 QCCD 아키텍처는 이제 그 트랩이 있으면 이 아이언들을 아까 마음대로 움직일 수 있다 그랬잖아요. 그래서 얘네들을 이렇게 여러 개를 레지스터를 놔두고 필요한 데에 데리고 와서 여기서 게이트를 하고 그다음에 다음에 필요한 애를 데리고 와서 이렇게 막 아이언을 계속 셔플을 해가지고 우리가 이런 서킷을 만들 수가 있어요. 근데 이런 서킷의 아키텍처를 지금 쓰는 게 소위 말하는 그 컨티니엄이라는 회사가 있습니다. 그것도 아이언 트랩 하는 회사인데 걔네들은 이런 아키텍처를 써가지고 쉽게 말하면 그 퀀텀 컴퓨테이션을 2큐빗 오퍼레이션으로 entirely breakdown을 해가지고 그런 걸 하는 아키텍처를 만든 그런 아키텍처를 쓰는 회사가 있습니다. 예, 그런 기술도 있고 저희는 그거보다는 버스가 넓은 뭐 32개 정도의 큐빗을 동시에 해서 컴퓨테이션을 효율적으로 하는 게 목표인데 이쪽에서는 이제 셔틀링 같은 걸 통해서 2큐빗으로 게이트로 브레이크다운하는 걸 그런 한 실험들이 있고 제가 조금 더 좋은 비디오를 보여줄 수 있는데 지금 이 슬라이드에 없어서 그런데 이런 여기 더 있나? 그래서 이런 경우에는 예를 들어서 우리가 여기서 제가 하이퍼테티컬 여기 32개의 큐빗이 있고 여기 32개의 큐빗이 있어서 이 사이에 컴퓨테이션을 마음대로 할 수 있어요. 그 다음에 여기에 16개, 여기 16개 우리가 다 잘라내가지고 얘네를 붙이면은 또 중간에서 32개짜리 컴퓨테이션 할 수가 있거든요. 그렇게 하면 우리가 이제 컴퓨테이셔널 개수를 64개까지 늘려주고 얼토 커넥티비티는 조금 떨어지지만 피스와이즈 얼토는 할 수 있고 이제 그런 아키텍처를 생각할 수가 있습니다. 그렇게 해서 큐빅 개수를 늘려주는 그런 시스템들은 저희가 고민을 많이 하고 실제로 개발을 연구를 하고 있고 그다음에 두 번째는 이 광학을 포톤을 이용하는 건데 여기는 이제 이쪽에 메모리 A가 여기 있고 메모리 B가 여기 있을 때 우리가 이거 두 개 사이에 엔탱글먼트를 만들어 주는데 얘네 둘이 트랩 안에 같이 있으면 엔탱글 쉽게 할 수 있는데 아까 소렌슨 같은 거로 얘네들이 두 개의 챔버에 따로 붙어 있으면 우리가 얘네를 가져올 수가 없잖아요. 그럴 경우에 어떻게 인탱글먼트 제너를 살 수 있을지 고민을 해보면 우리가 얘한테서 광자를 하나 만들어내게 할 수가 있습니다. 그래서 A하고 C가 그 원자 A하고 광자 C가 나오는데 우리가 이거를 그 만드는 데 있어서 이 메모리하고 광자 사이에 인탱글먼트를 만들어줄 수가 있어요. 근데 그거 우리가 이쪽에서도 한다면은 그게 이 아이언 포톤, 아톰 포톤, NV 포톤, 퀀텀 더 포톤 이런 인탱글먼트들은 지금 벌써 20년 전부터 이제 데몬스트레이가 많이 되기 시작했고 이거를 우리가 두 개를 만들 수 있잖아요. 그러면 그 다음에는 여기서 이 포톤들을 가져와서 이거를 50-50 빔 스플릿에다가 간섭을 시킨 다음에 디텍터를 해가지고 이 디텍터 두 개가 같이 클릭을 하는 상황을 만들어주면 그러면은 이 디텍터가 클릭하는 순간 이 원자하고 이 원자가 인탱글이 되게 됩니다. 이제 그런 실험도 이제 2007년부터 아이언은 이제 저 크리스 먼로 교수님이 2007년에 시작해가지고 다른 시스템에도 데몬스트레이션 많이 됐거든요. 그럼 이렇게 되면 이건 뭐냐면 우리가 이 원자 두 개가 직접 인터랙션 하진 않았지만 포톤 두 개를 내밀어 가지고 그 포톤의 인터피어런스 속에서 인탱글먼트 제너를 했는데 이게 그 헤럴디드 인탱글먼트라 해서 이 디텍터가 두 개가 클릭하는 순간 우리가 이 두 개 사이에 인탱글먼트가 만들어졌다는 것을 디터미니스틱하게 알 수가 있습니다. 그래서 중간에 포톤이 러스가 되거나 이런 에러들이 있을 때 그런 것들은 전부 다 페일러로 가고 성공을 하는 순간 왜 석세스를 했다는 걸 알게 되는 그런 프로토콜을 만들 수 있는데 그렇게 하면 이제 이거 두 개 사이에 인탱글먼트를 만들 수 있고 그 다음에 인탱글먼트가 만들어진 이후에는 하이 퀄리티 메모리에 이게 남아있기 때문에 우리가 이거 스토어했다가 나중에 쓸 수가 있습니다. 그래서 이제 저희가 생각하는 거는 스케일러블하게 이 퀀텀 컴퓨터를 만들려면 이 레지스터에다가 아까처럼 리니어 체인 레지스터에다가 이 커뮤니케이션 큐빗을 하나 만들어요. 근데 이 커뮤니케이션 큐빗의 그 유일한 목표는 포톤을 에미트를 해가지고 인탱글링 포톤을 싱글 모드 5에다가 보내주는 겁니다. 이제 그렇게 하면 이제 그 다음에 우리가 그 이런 유니트를 굉장히 여러 개 만든 다음에 여기서 나온 광자들을 우리가 광 스위치를 통해서 우리가 원하는 페어 사이에 인터페어런스 할 수가 있는 거예요. 예를 들어서 우리가 이 첫 번째랑 이 마지막 거 사이에 인탱글먼트를 하고 싶다. 그럼 여기서 나온 포톤이랑 여기서 나온 포톤을 스위치를 통해서 인터피어런스에다가 집어넣어주면 디텍터가 두 개 클릭하는 순간 여기하고 여기 사이에 인탱글 페어가 생기겠죠. 근데 우리가 그거를 이 스위치를 잘 조절해주면 arbitrary 페어 사이에 인탱글 페어를 만들 수 있습니다. 그래서 그거를 활용을 해서 이 큐빗 유닛 이런 유닛들 사이에 그 양자 정보를 통신을 커뮤니케이트 할 수 있게 되고 그렇게 만들면 우리가 굉장히 스케일러블한 시스템을 만들 수가 있습니다. 그래서 사실 제가 벨랩에 있을 때 이 1000포트짜리 옵티컬 스위치 만드는 경험이 있기 때문에 우리가 이 정말 아까 말씀드린 대로 집적도를 높여서 이런 양자 컴퓨터 하나가 아이언트랩 양자 컴퓨터 하나가 진짜 이렇게 데스크톱 박스에 들어가는 정도가 된다면 이런 거 1000개 정도를 만들어 가지고 다 엮어서 굉장히 라지 스케일 퀀텀 컴퓨터를 만들 수도 있다는 이제 그런 것들이 이제 가능하기 때문에 이거 전부 다 기술 개발 문제입니다. 기본적인 원리는 전부 다 베리파이가 된 거고 이걸 어떻게 시스템으로 잘 만들어서 돌리는지 그런 게 중요한 문제가 될 것 같습니다. 예.
그러니까 바이어스 원리 시스템을 넘어가기는 좀
뭐 힘들진 않고 사람들이 많이 생각을 하고 있는데 이게 원디처럼 보이지만 실제로 오토 커넥티이기 때문에 예, 이게 굉장히 커넥티비티 수준 높습니다. 예, 그 지오메트리컬리 원디라고 해서 실제 연결도가 원디인 게 아니기 때문에 그렇게 생각하시면 안 될 것 같습니다. 여기까지 하고 또 질문이 있으신 분들은 제가 잠깐 여기 더 머물러 있을 테니까 하시고 예, 오늘 긴 시간 경청해 주셔서 감사합니다.